So, good morning, everyone. We're just this morning going to look at energy efficiency in Volume 2 of the NCC. You'll notice up on screen here, this document says BCA 2009. So the regulations that are current at the moment in the Northern Territory for energy efficiency in Class 1 buildings refers you back to the BCA of 2009. That's because the Northern Territory, the way we have state and territory variations within the NCC, when you read the state and territory variation for this, it will refer you back to the 2009 version of the BCC. And that often happens in the NCC, that some states will say, oh, where the regulations were at back in 2009, that's what is current for us right now. We haven't gone up to the next level. So when we think about energy efficiency and housing in the Northern Territory, there's been a lot of talk and public knowledge about having a 5-star energy rating for our houses. How many of you have heard about a 5-star energy rating for housing? Yeah?
I didn't expect that.
Last week, okay, all right. So maybe it's not as widely known about as I would have thought. There's been a little bit of articles in the newspaper that over the years about 5-star energy rating. So last week when we talked about the NCC, we talked about a deemed to comply method of compliance, which is quite prescriptive and takes you step by step on what you need to do in the building to be compliant with the NCC. And we also talked about a performance solution for compliance with the NCC. When we think about energy efficiency, it's a really good one to explain the difference in these two, because today we're going to look at part 3.12, that's volume 2 of the NCC. And when we look at that, that's a deemed to comply method of compliance, and we will go step by step through all the things that we need to comply for energy efficiency. And then we can compare that to later, when we go through step by step, then later on I'm going to compare that to like an energy model. We're not going to look at an energy model, but that's what the performance solution is. It's an energy model, and the energy model looks at the building as a whole rather than in parts of the building and how it complies. But that will make more sense to you later on. So energy efficiency section is broken up into 5 sections. The first one is about the building fabric. The second one is about external glazing. Third part is building ceiling. The fourth is air movement, and this is where we do our calculations on ventilation, and that we touched on last week. And then the very last part is services. We'll get straight into it. So you can see here that these are the state and territory variations that you read at any section of the NCC. Who does it apply to? Where is it current, and what version of the NCC is current in what state and territory? Those are sort of those questions. And every chapter of the NCC has this in place. Okay, it says here for this one that the NCC at the time of 2009 in the Northern Territory, part 3.2 is replaced with BCA part 2005 part 3.12. If you're not seeing this in front of you on your current version of the NCC, which I assume you're not, it's because the Northern Territory are not compliant with what's in the current version of the NCC. In the Northern Territory right now, we are still compliant with 2009 version of the NCC in terms of energy efficiency. We're only 9 years behind where we should be in the Northern Territory, which is, pretty standard for the Northern Territory to be not up there, especially when it comes to energy efficiency. You can see here that a variation for New South Wales. New South Wales have another way of complying with energy efficiency, and they don't do the 5-star ratings at all. They use a system called Basics down there. So they're exempt from compliance with the NCC for this particular thing, but they do have other measures in place. Well, I don't want to get too far into that because it gets a little bit confusing. It's sufficient to know that we need to be compliant with the 2009 version. So for this, in any normal office, we would probably have all the older versions of the NCC either in book form like I have here, or you might just have downloaded all the older versions, because sometimes when you read the current version of the NCC, it's going to tell you that in the Northern Territory the compliance for that chapter is going to be in the 2009 version, and you're going to have to flip between versions of the NCC. Okay, so building fabric. So the first part is to do with roofs. And for roofs, it's telling us, so these are climate zones. And actually, I should bring up a climate zone map and show you this first and foremost. So as we all know, Australia is a huge island and it has lots of different climates on the one island. This is the climate zone map that's associated with the NCC, and it's just split into different climate zones. So we happen to be in this orange band all across the top of Australia, which is climate zone 1, easy to remember. Climate zone 1, we're high humidity summer and a warm winter. And then as we progress down through, it pretty much flows this way, if you could see that little key in there, which you can do in the paper copies, or if you download the whole PDF, it tells you which zones are which, but according to colour. So we've got different ones. We've got warm, humid summer, mild winter, climate zone 2, which is this sort of Alice Springs area. And that's generally the Northern Territory. It looks at climate zone 1 and climate zone 2. As you move further south, there's all different ones: cool temperate, mild temperate, alpine areas. Yes?
Where did you get that map?
I just Googled NCC climate zone map and it brought that up for me, but it is in the very front of the NCC. But it's on that Australian Building Board's website. Let me see if I can get the zone map up a bit better. So zone 1, like we said, is that what we really think of as the tropics. This is the Tropic of Capricorn. So anything above that line is where we spoke last week, where the sun actually goes around all sides of the building. Below that, you'll only get sun in the northern sky. Excuse me, frog in my throat this morning. I still can't read these zone maps. They're a bit blurry on the screen, but you will, if you have a PDF there on your screen, you'll be able to read them. So, when we're thinking about the Northern Territory, Darwin in particular, we will concentrate. Oh, it zooms for me too. There we go. So we've got different zones. We've got some zones in here. Zone 5, Zone 6 is around Victoria quite a lot. Zone 7 is the actual alpine areas, so you know, the snowy mountains and all of that up there. So obviously when it comes to energy efficiency, the climate has a huge part to play in that, and influences how we address energy efficiency in our buildings. So I'm going to pop back over here now, and so on our table for roofs, we're looking at climate zone 1, and we're looking at what the minimum total R value is. R value. Does anyone know what R value means? So R stands for resistance, and it's the rate of heat flow through any material or any particular thing. So that's what R stands for. The higher the R value, the slower the heat flow through a particular material. So climate zone 1, we're going to say for roofs, we must reach our roof construction, and this is talking about all the parts of the roof and ceiling construction. They have to reach a minimum total R value of 2.7. And the direction of heat flow, downwards. The direction of heat flow in the colder climates, so down here in the alpine climates, is upwards. Okay, let's think about this for a minute. If you're in Darwin and you're underneath the roof of your house, where's the heat? Outside. Okay? So the heat wants to flow downwards. So the heat wants to come inside, coming down. If you're in the snow and you're inside your house, where's the heat? it's inside and it wants to try to flow upwards. So that's why there's a difference between downwards and upwards there. And of course, I'm always very happy I don't work in one of these areas where they get a downwards and upwards heat flow depending on day and night and seasons and all the rest, because they're really difficult buildings to design for. At least for us, we only have a heat flow in one direction, which makes it a little bit simpler. So that is downwards, so that's important to note.
So we'd be looking at Alice Springs, so downwards, upwards.
Yeah.
Zero to
Yeah. And huge diurnal, is that the word? Diurnal, his range is what that's called. Big difference in temperature from day and night. Okay, so for roofs we've identified for us, it's going to be R2.7. So, I'm going to read through this because we'll probably hit on lots of points here that we want to know. So the roof space ventilation option. In climate zones 1, 2 and 3, that's us, 1, applies to a pitched roof with a flat ceiling to ensure that efficient cross-flow ventilation is achieved in the roof space to remove hot air. So you get in the NCC you get a concession. You can minus, so the total we want is the 2.7. You can minus some concessions off the 2.7 if you do different construction types. One of them is that you can have a light colour roof. I'm just going to read this bit down here. A light coloured roof reduces the flow of heat from solar radiation better than a dark colour roof. A roof with a solar absorption value of less than 0.55, this is a solar absorption value of less than 0.55 means the roof is of a light colour such as white, off-white, cream or dull zinc aluminium. Typically absorption values based on this particular code. So if we say that we have a white roof, we can also get a concession off the 2.7. So instead of having a total R value of the 2.7, we can say minus 0.5 for light coloured roof.
Sandra, all of these numbers have actually changed in the 2016 table.
They will have, and that's very true, but we don't need to comply with the 2016 table. We only need to comply with this one. Because we are applying it from a code that was back in 2009. That's the one we're still using in the Northern Territory at the moment. So you're very right. Because like we said last week, the NCC is trying to improve us all the time. And so let's hope that next year when the NCC comes out, 2019 version, that the Northern Territory have decided to up the game a little bit and make it a little bit more difficult to comply with this code, and so we therefore get more efficient buildings. I've heard that that's not going to be the case, that we're remaining with the status quo. So this is the code I think that we will be using for quite a while. So does everyone understand this part here about the total absorption value? So obviously if you've got a white roof, it reflects the sun a lot better. So less heat goes into the building, okay? Don't worry too much about absorption values. You will use this table quite a bit to just look them up anytime you want to know. So if you get a set of plans and you have to do the energy efficiency deemed to comply calculation on it, you will need to know what the colour of the roof is going to be able to do that calculation, and the walls as well. And I just want to make it very clear the principle of that, so that if you've got a very dark coloured roof, that's not such a good thing in a tropical area where you're trying to reflect heat away from your building. You don't want it to absorb into the building. Okay? And so you only get the 0.5 R value concession for a light coloured roof if your total absorption value is less than the 0.55. So we can see we move away from that very, very quickly. You've got light cream, is at 0.3, off-white, light grey, galvanized steel, and then your zinc aluminum that we're all quite commonly used to seeing, which is the piece of material over there that we have, the piece of roof colour bond custom orb. Once we get past zinc aluminum really, and get into the yellows, reds, or any, what I say to people, anything that you can call a colour, you know, if you go through the colour bond range of roof materials, We have my little colour bond swatch here. These are all different colours of roofing that you can get from Colorbond. All these pieces of steel here that is your roofing can come in a wide range of colours, and people often want to do different and dramatic things with colour on their houses, and often the covenants of new suburbs will require them to do that. You can pass those around if you want. They're all different roofing and cladding colouring. But yeah, solar heat gain coefficient numbers on the back of the Colorbond colours, or you can look them up on their Colorbond website online. It'll give you a table like this with all the different colours and what their absorption values are.
One thing you have to take into account though, a white roof will discolour over time, especially with the wet season, so it's got to be cleaned more often than one that is slightly off-coloured.
Probably it gets just as dirty, the off-colour one, you just can't see it.
Yeah, because I know that one of the white roofs we had to clean pretty much every 2 years, whereas the one that was more of a green, off-shaded green, but not a darker colour, which is less because of our wet season and gathering of moss and stuff.
No, that's that may be so, Paul, but for this purposes, we're really talking about the colour at the time of the construction. You know, that's what these calculations are all made of, are all built from. I'm just seeing how much of this we need to read out and how much not.
So why is it that some people put in those real dark colours in? Is it obviously just for the look?
Aesthetics, yeah.
Because there's a lot of buildings going up now that have got real dark reds and the dark green or the black.
Really?
Yeah.
A lot?
Being repainted and stuff.
Yeah, with navy blue.
Navy blue, is it?
But the tile blue, and our house is white, so it will be really weird. That is white roof. Yeah.
Yeah. And the White House, yeah.
You just have to work so much harder. That's very cool. And it's really hot. You can tell? Yeah. Oh, yeah. Yeah. And we've got a lot of concrete as well in our, so wow. And like trouble to cool down. Yeah, it'll be warm. Enough ventilation.
Tile roofs on the out up here now.
Yeah.
They're on the out because you can't buy.
Yeah.
Can't buy locally made tiles. And trying to find a roof tiler up here is nigh all impossible as well. I had a case of a house that has tiles on it having some roof leakages, something I was looking after, and I really could not find a roof tiler up here to come and repair some tiles.
That was a big thing in the 80s. All the Western Australian companies come up and then they had that batching plant here making the tiles. But you never see anybody putting.
No. This is a very typical roof construction for Darwin, so we'll have a look at the calculation for this one. So what we've got here is we've got metal cladding on the outside, and so the lighter line here is just showing you the profile. We've got roof framing, so this is the actual roof structure here. It could be a rafter, it could be a roof truss. The structure is not particularly relevant to this calculation. It's more about the actual build-up of this. We've got an unventilated roof space in here, and then we've got the bottom chord of the truss, or perhaps just some ceiling framing if there's no truss in place, if this is just a rafter construction, and then we've got the ceiling lining here, so the ceiling's on the battens there attached. So when I talk about the roof structure, this is what I mean. All of this area right down from the underside of the ceiling right up to the outside of the roof when you're trying to do an R-value calculation. That's what we're looking at. And so the figures associated with that we've got the metal roof. So sorry, I'm just trying to see how they've done this here. So they're saying to us for a metal roof, the total R value of the roof and the ceiling materials is only 0.5. Normally I would do that whole calculation out, and so they're saying the minimum added R value of insulation needs to be 2.17. Okay, can you see that there? So it's this column here that we're looking at, and they're saying that sketch that we just looked at for the total of all of those materials, and you can do a very complex R value calculation where you calculate out the R value of each of the materials and all of the air gaps associated with that, because insulation is about trapping air. Basically, when it comes down to it, insulation is about trapping air. When we look at insulation products, such as Sisolation, these type of products, and even bulk insulation like this, it's all about the air pockets in those materials. That's what gives you an R value, and that's what slows down the rate of heat flow in something. So something like the actual metal itself has hardly any R value. I think the R value for the actual metal is 0.1. So it's not giving you any resistance at all. So what are we going to put in this structure? If we think about a tin roof, it's really got no air gaps in there. We've just got the metal decking. We've got this structural frame that, maybe timber, but that, the frame, if we think about, our model's gone, but if we think about a frame, the frame isn't consistent all the way through. The only thing that's been really consistent so far is the metal and maybe the plasterboard on the ceiling. Those are the only two solid, continuous building envelope materials that we've got all the way around. So what else are we going to add to that to give us an insulation property and to give us some air gaps to slow down the rate of airflow? So we can assume we have a light coloured roof. So that's going to give us the total R value that we want then is going to be 2.2. Does everyone understand that this is a concession? That's the concession of 0.5. And the NCC tells us that if we use a light coloured roof, it's trying to encourage us to use a light coloured roof. And if we use a light coloured roof, we only have to achieve the R value of 2.2. If we don't use a light coloured roof, we have to achieve the 2.7. So you need to put in more insulation. You can have a dark coloured roof, but you need to use more insulation. So obviously the most cost-effective method of insulating is to use a light coloured roof to begin with. The less insulation required. And then it's telling us, the NCC is telling us that the total R value for that roof we described is 0.55. This one? Oh yeah, sorry, I'm on the wrong one. Yeah, 0.53. So we can get 0.53. So we need to required insulation.
So that's what our insulation's got to, minimum's got to add up to.
Yeah. Now when you go to buy insulation products, when you go to buy a product like this, it will have and we are having a person coming in to talk to us about insulation next week, so I'm not going to go too much into this. When you look at Sisolation, if you lay that Sisolation flat and you have tin here, and it's pulled tight underneath the tin, it gives you an insulation value of, I'm trying to think what it is, it's about 0.7. If you leave an air gap, so if in between the battens this sags down in between each batten, this is the correct way to install Sisolation, and it has an air gap between the Sisolation and the tin. And when you add the air gap, you can achieve like 1.5. It's a huge jump because the air that is the gap in between there is giving you the insulation value. So when you read the marketing on this, it will say in really big writing, can achieve R 2.5 for roofs, okay? And builders and designers all the time go in and say, oh, I can achieve R.2 in my roof by installing isolation. It depends how it's installed. And when you read the small print of the manufacturer's data on this, it will tell you how it needs to be installed to achieve the R 2.7 or whatever the marketed value is. And for depending on the pitch of your roof, depending on all the different build-up of your roof, all of those things, the R value changes, okay? So if you've got a warehouse roof with no ceiling, for instance, that's a different calculation. So for every single different roof type, it's a different calculation for the R value of the roof, okay? But minimum standards say that for a roof to comply, it needs to achieve R 2.7. But with a light-coloured roof, that's reduced to 2.2. All you need to know for now. So there are different calculations you have to do for roof lights. I'm going to just mention that it's there in case you ever work in a jurisdiction with roof lights, because obviously roof lights are a very weak point in the roof, and there are different requirements for that. We use them. I've never seen a roof light used in Darwin, so I'm not going to spend any time talking about roof lights for this jurisdiction.
What do you actually class as a roof light? Talking about skylight?
Skylight, yeah. Correct architectural term is a roof light, but yes, skylight. Any glazed element that forms part of your roof structure.
There's quite a few in Bellamac, actually.
Yes,
I don't know what they were thinking, but when you wander around in the evening walking the dog, you can see the
light
really easily because they let the light out.
Yeah.
In the night time, rather than bringing the sun in during the day, they actually let you have artificial lighting on, and you can actually see the lights.
Yeah. If you ever do come across that you have to put a roof light into calculation, the basis of it is that you have to work out the area of the roof and the area of the roof light and get a percentage of that, and then you have to do a calculation that increases the R value of your roof to make up for the loss of R value where the glazing is.
Because the units up the road, they've gone skylights and LEDs in the units. I didn't notice that until the other day when the guys were up on the roof.
We spent so much time and energy trying to shade our windows in the walls. I don't know why someone would think it was a good idea to put a glazed element in the roof.
Well, it saves having a couple of lights inside. In like a hallway or a bathroom. You turn that light.
It gives you natural light. Absolutely, it gives you natural light, but like if you're talking about energy saving from lights, it wouldn't be a very small percentage of the heat gain and the cooling energy you're going to have to use to negate the heat gain through that roof element. It's obviously being done. So external walls, it's quite similar for external walls. Depending on which elevation you're on. So there's lots of talk about which orientation you're facing with your walls. So for climate zone 1, our walls need to achieve a total R value of 1.9. I should have kept my writing a bit smaller. That's roofs. And for walls, it's R 1.9. Or, option B, you can achieve 1.4, a total R value of 1.4, but it must be constructed on a flooring system that is in direct contact with the ground, such as a concrete slab on ground or the like. So remember we said our block-built houses, which are built on a concrete slab on ground construction, they have a little bit of extra benefit because the ground is a cooling source. And so the slab of those houses, slab on ground houses, stays cool because it's called earth coupling and ground coupling, and the heat transfer from the cool ground underneath the house, which is continually in shade because it's now underneath the slab, is rising up through the slab, and it's actually having a cooling benefit of the house. An elevated house such as our project won't have this benefit, so we won't be able to reduce our value to the 1.4 there. We'll still be with the A option of 1.9. So when you build a concrete block, slab on ground, your walls only have to have an R value of 1.4. And then C, for a masonry external wall with a surface density of not less than 220 kilograms per meter squared, shade the external wall of a story with a veranda, balcony, eaves, carport, or the like. So this is one we often use for blockwork homes. Blockwork homes do have a surface density of not less than 220 kilograms per meter squared. And so we look at, and again, this comes back to the idea that our north and south facades are quite easily shaded. So they have to have a projected minimum angle of 15 degrees only. But however, for our east, southeast, southwest, west, and northwest orientations, that angle of projection needs to be 45 degrees. I'll show you what that's all about, the degrees. If you have a house here with a little bit of an overhang on your wall, if you take an angle here of 15 degrees, so this is your 15 degrees here, then your overhang must come out as far as that 15 degree angle, okay? And this is for your north and south elevations, okay? So that's north and south. For all other elevations, that angle needs to be 45 degrees. So let's draw the 45 degree. Now our angle of our roof projection has got to be much greater. So the angle is from the ground. Any questions on that? So what it's telling us is that for all the other elevations, really we need a veranda or a carport, something that extends quite far out. And for the north and south, we need a much shorter angle. My 15 degrees could have been a little bit more. Like that. And so in general, your 15 degrees, if you draw that out with a bit of geometry, the distance of that projection is about a meter. For a single story. Of course, when you go up a whole other story, you've got a story down here that's not protected at all, unless you do some other sort of spandrel panel or just over the window or wall type shade system. Yeah.
Why is it that we have a minimum of 900 for our eaves?
We don't have a minimum 900 for our eaves. We can have eaves of 300 if we want.
No, but if we need to get that angle.
Yeah.
But a 900 overhang for scuttering.
We'll give you that. Yeah.
No drama.
Yeah, there's not many places up here in Gallery.
By the time you've got the colour bond and then you've got the fascia and things, you're there.
Yeah. 900 will achieve it. 900 overhang of the structure will achieve the shadow line of a meter.
That's what I was getting at,
Yeah.
As long as you have a full
Yeah.
house.
But remember when, so this is saying that if you do all of these things and you've got block work because you've got to have the surface density, and you've fully shaded all the walls. Now, I don't know many houses that have full shading on all of the walls. First of all, you'd have to be single story. If you're double story, you're not going to achieve that with roof overhangs alone. Because remember, once you, let me just watch this one out. What Nick was saying, and he's very true, is if that's a 2-story house, and that's your first floor level. And ground is at that location. If you draw your 15 degrees, sorry, I'm not very good at drawing 15 degrees. You haven't achieved it with that roof overhang if it's 2 stories. Okay, so if you've got single story, ground level, blockwork home, fully shaded walls, blockwork construction, then you don't need any insulation, you don't need any R value in your walls. Remember, this is the 2009 compliance standards, and I think it's very lean. I don't think it's got a lot of meat to it, but we do need to look at it in terms of what insulation we do need to apply to our particular project. At the moment, which of those do you think is applying to our project? Elevated house. The 1.9, we're still up at the 1.9. What's in our walls at the moment? Weatherboard, timber, plasterboard on the inside. That's it. That's our sandwich. Mhm.
So your tin is going to absorb more heat than the weatherboard.
Yeah.
Say tin, you mean colourborn custom.
Yeah,
that's what you mean.
Yeah.
I don't think we've made
Metal cladding. Metal cladding. Metal cladding. We can just call it metal cladding because.
You might have to come up a couple of
Yeah.
centuries.
Yeah. So in the NCC, it is referred to as just metal cladding. Okay, we can replace the tin for metal. Yeah. So metal cladding, as I said, very, very conductive. You know, it conducts the heat right through. You know, you're sitting in a baked bean in a little tin box, metal box.
Achieving 1.4, that is using where?
With the 1.4?
Yeah.
That's with B, you have to also have the option here of having direct contact with the ground, such as concrete slab on ground.
1.9. B
That's the
is
basic.
Yeah.
slab on ground concession plus 1.4.
Yeah.
It's a different
Yeah.
way of doing it.
It's not particularly straightforward, this part of the NCC. There are lots of different options in there, but you see a first step is to identify what our project, what is it, which option is it.
It also seems really easy to go overboard and make a very efficient place. If you incorporate all the rules, they're not huge asks.
No.
A 900 or 1 metre overhang. If you've got a slab and an overhang of a metre, you can get that up really quickly.
Yeah. As I said, this isn't telling you you've got an energy efficient house. This is just telling you you're compliant with very basic minimum standards of energy efficiency in the NCC. So there is an option D there for weatherboard sheet clad, which will be us with sheet metal, masonry veneer external wall. So that you have to do 3 things here. You have to incorporate reflective insulation with an emittance of not more than 0.05 inwards, and be constructed on a flooring system that is in direct contact with the ground, such as a concrete slab on ground or the like, and shade the external wall of the story with a veranda, balcony, eaves, carport or the like, which projects a minimum angle of 15 degrees in accordance with. We'll look at that figure in a minute. It's probably much better than my diagram. So this is another option for us. So I'm going to go to this point first, point 2. It's got to be slab on ground. Have we got slab on ground? No. Can anyone guess what this house is made of? What's the construction?
The one we're using.
No, this option, no, not the one we're using, this option D. When would you use this as your option? What type of house would you be building? You all have a chance to read it there.
Is it an example of one?
Yeah. You explain. So tell me what the slab is made of. Tell me what the walls are made of. Tell me what the roof overhangs do. In simple terms, and not in NCC terms. In just very simple terms, what is that?
Well, that's a framed wall because, again, we briefly...
Correct. We've got framed walls, yep. Framed walls. What's the slab? Concrete, slab on ground. Framed walls. And we've just got an overhang of 15 degrees, so if we have 900 eaves all the way around, okay? If we can do all of those things, all we have to do is incorporate reflective insulation, this type of insulation in the walls. We don't have to make up a particular R value. We just have to have all of those different things, okay? So, you know, when we look at this and we think tropical elevated houses, we're right up the top. We have to get to achieve a total R value of 1.9. That is because they're very lightweight houses. What's in them is not a whole lot of material or density or mass to protect us from the elements. They're very much a shell, and they sit up high in the air, so the warm air is on all 6 sides of the cube, you know. It's over the roof, it's under the floor, it's on all 4 walls. Whereas if you've got slab on ground, you've got heat on 5 sides. And that makes a big difference to energy efficiency, you know, the area of your building envelope. So heat transfers through the roof and the walls, but it doesn't transfer through the floor anymore because you've got your ground coupling with your slab on ground. And this is telling you that that's giving you benefit and giving you concessions for it. Okay, so we have ruled out this option because we're not slab on ground. We're not blockwork, so that's not going to be of any value to us. And we're not slab on ground, so B, again, we can't apply. So we are left with complying with A, which means our walls have to make up R1.9. And it should, and these are for all the other top climate zones. So in every single climate zone is different. This is a really good diagram of the shading projection. So there's your 15 with your shorter overhang. And of course, depending on the level of the internal floor and the line of shadow, we call this the line of shadow given by this, you have to determine whether or not your angle here is 15 degrees or less. And then, of course, 45 degrees or less. And so often this is, when you're drawing, and you'll see this is much easier to do in something like AutoCAD, when you draw your building, and then you just draw a line off at 45 degrees, sometimes that will tell you how wide your veranda has to be, or how long your overhangs have to be to comply with this clause. It's a drafting exercise that very easily done. It looks a bit complex up there, but once you've got a drafting tool in front of you, it's a pretty simple thing to do.
So it's not from the ground, it's from the internal floor.
It's from the internal floor, yes, but if you do have another floor underneath here, you don't have your 15 degrees for the ground floor.
So you don't have to have 2 little...
You'd have to have another little eave coming out here, but nobody ever does that on a house. So basically you're saying if you've got 2 stories, this can't apply. It really only applies to single stories, or unless you're going to be, maybe you've got some balconies off that first floor level that can overhang at the ceiling level of the ground floor. And then you're getting an overhang there as well.
That explains why I've got the 2 most useless balconies in the whole world in my house.
On your house, maybe, hanging out over to shade. They're providing shade to the ground below. But that's very difficult to achieve all the way around the house. Really, I don't see too many houses with balconies that wrap around at first floor level. You often see it at ground floor, but not first floor. So obviously you don't have to do that. It's just if you are already doing that in your design, that's, like we said, that's kind of passive design. You know, you're designing the layout to suit for shade. But, you know, if you don't achieve all of that, you can go back and apply one of the other rules, like we have to get the R1.9. So remember, this rule doesn't apply to us at all because we're not in any of these concessions. So once the concession doesn't apply to you at all, this one, once you're not using blockwork, that doesn't apply. Do we understand that? Everybody looks very confused, and I'm a bit loath to move on while everybody's looking so confused. Please ask me lots C can only apply where we've got blockwork. Really, basically, single-story blockwork, and then we can apply the shading rule. The walls are shaded. Where we've got an elevated house, it doesn't matter if our walls are shaded or not. We're going to have to apply our 1.9.
When we're referring to blockwork, we're talking about lesser blocks as well as bricks.
Yes, masonry construction. Yes.
It doesn't matter whether it's a single or a double.
It needs to achieve a surface density of not less than 220 kilograms per metre squared, which I've been told by a structural engineer basically covers all of our masonry applications.
So even brick veneer.
Yeah, yeah. Yep. Okay. So how do we achieve 1.9 in our walls? See where our diagrams are. So we've got one here that's just got weatherboard on the outside. So this is the outside of the wall, weatherboard. You've got some sort of framing in there, and then you've got plasterboard. So if you think you're like a little molecule of heat, what do I have to get through? I've got to get through the weatherboard and the plasterboard. This one is just showing you a fibre cement sheet on the outside and plasterboard. I'm trying to find one that just has a metal cladding on the outside. Sure there is an example of that one. What's that?
Would be the only ones that put
Yeah, I know, yeah, and this is written for the whole of Australia, so it may not be us. So we just use the one that will be nearest to it, really. Which one of these have you used before, Lisa?
Pardon?
Which calculation have you used before? This one, B, cement or metal sheet.
Yep.
Yeah. It just doesn't give us a diagram of that one. So it's telling us where we have the metal sheet and just plasterboard on the inside, we can achieve a total or R value of 0.41. So that's all that wall is giving us. So can you see that if you build a house and you just have metal cladding and you have plasterboard on the inside and you've only just some framing in between, that your R value for that wall is only 0.41. That's a long way from 1.9, what you're supposed to be achieving. Of course, most people will put isolation in the walls, but it's actually not enough. You need to put some bulk insulation as well. By bulk insulation, I mean like a fiberglass insulation or a rigid insulation like this. A bulk insulation, the easiest way to remember is this is what I call a reflective foil insulation. It's more like a membrane. It relies solely on the air gaps. Sometimes it's got little bubbles inside it that trap air gaps inside, but it also relies on the air gaps around it, top and bottom, to get an R value. Whereas a bulk insulation always maintains its own thickness. With fiberglass, you do see people constructing with fiberglass and they squash it, and then it's no good anymore because it must maintain its thickness. It's all about the air that it's trapping.
that product you got there,
Yeah.
the foil one, the one that's added to it.
Yeah.
Is that common to use that on the exterior walls? Because most of them just have plain.
Yeah.
Plain.
So sometimes what Paul is referring to there is sometimes you can see this product. You see that that's got air bubbles inside it. Sometimes there's just a single layer of that without the air bubble. Sometimes that's just a paper, a reflective foil on its own that's being used. That product has the least R value This is slightly better because it's got 2 layers of reflective foil and it's got some air bubbles in between. But even with this product, it can't be flat against the wall. If it's flat like that with no air gaps, if for instance you sandwich that in between 2 pieces of plasterboard, for instance, I don't know why you would do that, but you might, and you said, I've got my insulation in there, it's sandwiched hard up against it. I've certainly had builders tell me how neat and tidy and how tightly they've pulled this between the battens. I don't want to hear that. I want to hear that they've sagged it, they've trapped air in between it. And there are little things you can get called spacer biscuits. So if you think when you're putting your plasterboard up, for instance, say let's say we had this blockwork wall, and let's say we put battens on the wall. And we want to insulate it, we want to add some more value to this wall, and we put some battens on it. And you come along with the isolation. Let me grab a batten while I'm here.
So would it be that the knowledge now is a little bit more up to date, because I remember putting that isolation up, and like you say, tight as possible like a drum, and that's what we were told to do.
I still see it like that on building sites all the time.
Yeah, because you can still see some of those places.
So lots of places will do that. They'll get the isolation, they put it flat against the wall, and then they'll put the batten on it. And then they come along and put the plasterboard. Oh, what side of that is out, like that. Now you do have an air gap there. The batten has given you the air gap there. But really, for this to get the best value out of this, you want an air gap of 20 mils on either side. So the best way to do it is put your batten up, put this up, and what happens is we put all these little sticky things called spacer biscuits. Just here, what does a spacer biscuit look like? It looks a little bit like this. Alright, and what that does is then when the plasterboard comes along, it holds the reflective foil away from the plasterboard, and it gives you the best air gap. And you've also got air gap on the other side too, because the spacer biscuit just holds it out. Because really what you want this to be is in the center of the cavity. You want it staying with an air gap on both sides. Mm-hmm.
You don't have to follow the instructions to get the recommended, like the stated R value. But do you know what I mean? Like, it's because the insulation states 3, but it has to be 3 at a certain installation. But going to the container, you can just say, oh, well, the cabinet says 3 at 3 without the installation.
No, that's exactly what I'm telling you. Well, first of all, it's not planning, it's the National Construction Code that tells you all this. So in the National Construction Code, it's quite specific about, it's all the National Construction Code tells you is the total R value you have to achieve. It's up to you to achieve that. Now, where you'll find it is, and again, I got James Pinion, is expert on this, is coming in to talk to us from Aircell Insulation and Kingspan, so Aircell is the reflective foil product they have, and Kingspan is their insulation board. It's a rigid board like this, like this one. So he does both types of the insulation, and he will talk to us about this. So it's up to you as the designer to construct in a way that will achieve the R value, the minimum R value that the NCC is asking you to do. It isn't done very well within the industry, I can tell you. But this is where detailing comes into it when you do a documentation set. You should really be drawing a section through the wall and showing where the insulation is to sit and how it's to be constructed. The easiest way as a designer to get the full R value of anything you're providing is to recommend a bulk insulation rather than a reflective foil isolation. Reflective foil isolation just has, because it depends on the air gaps, it completely is reliant on the builder to build it correctly on site, and it's, as I said, not done very well in many instances. Okay, so does everyone understand that we're required to have walls at an R value of 1.9? That was our option that we went with, and currently our construction is only going to give us 0. Where are we? Oh yeah, 041. And do you see that the 0.41 says, it's probably getting too complicated now, but including an airspace. So that, what is that looking at? It's looking at metal cladding, I'm going to use this, probably isn't the right stud for it, but if we've got metal cladding, and then we've got a stud, can I get you to hold the cladding for me? You might want to take a step up and have a look at this when it's constructed. You okay there? No, I think we'll really go all right. But I would like everyone to come up and have a look at this. This is the easiest way to. But this is our elevated house, okay? I'll just get you to hold that for me. Thank you so much for being my assistant. Okay? That is our elevated house. This is the external side. This is the internal side. We've got some sort of a stud. We might have, I think on this one we have timber frame studs. The studs and the structure don't count in an R-value calculation. Why don't they count? Because we're not trying to count the heat transfer going through here. We're looking at the heat transfer through here. Okay? So there's only studs every 450 centres or something, so it's not there consistently. We've got just this. So what do we need to put in here to give us the R value of 1.9 insulation? When we look up there and it says cement or metal sheet, option B there, it says 0.41 including an airspace. Which airspace is it including? This one. Okay? If we fully fill that, we lose the R value that was associated with the airspace itself. Do you know what I mean? So if I come along with a rigid board, these are wall insulations. Use the little ones. It'll be easier. These are rigid board insulations. If I come and do that, it'll probably give me the R value I want to achieve, but I need to minus the air gap off the calculation because I've fully filled the air gap. Okay, so that's what that's referring to.
But how do you know what the value of the air gap is?
Because we're just taking that as a number of 0.41, there is a way, and really energy assessors do these calculations, designers don't really do. You can get the R value of this, the R value of this, and then just add them. So you wouldn't have to mind, you can,
from 0.41 though?
Yes, minus it from 0.41 and then you know what the air gap was. Or you can just add them on their own and see what you have to add in as a bulk insulation.
But then you can just, if you didn't do that, you could just find insulation that is more than...
Yeah, find an insulation that's an R2 and fully fill with that, and then you know that you've achieved the R1.9. That's the easiest way to do it. Try not to get down into the, the 0.05s of the insulation, it's, for the sake of saving, very, very minor costs. Did everyone have a good look at that? You got it, guys? So that's your wall makeup.
So even with that insulation, you still need air gaps?
No, with bulk insulation that has... So if you have a look at that product, you'll see that it's quite foamy, so it's trapping air inside it. So it's already got the air inside. All insulation relies on air.
So do we normally use this for Darwin's area?
In dwelling houses, I normally see reflective foil, the other one, and fiberglass, which is a bulk insulation, but it's like a blanket, more like a blanket than like a rigid thing. It's softer and you can. So what happens with the fiberglass is that they can roll the fiberglass over the batten like this, and then they squash it where the batten is because they've got to fix through it. But then it's allowed to fill the cavity where there is a cavity. But it's...
Is this more expensive?
Yes, it is. It is. But it's a much, much better product. Much, much better. Couldn't recommend it enough.
So that solid foam
Yeah.
tin on there, how do you use that? Where would you use it? Is that in place of the outside tin? Does that go up in the front, or is that a totally...
Yeah, no, you're right. There's certainly lots of products on the market that are metal cladding that is bonded to some sort of insulation product. There's lots of varieties of them, and again, we're going to get a presentation on that next week. It's not commonly used, but it's probably the direction we're heading.
That seems to be fairly good.
Yeah, it's giving you all the properties.
Yeah.
Yeah.
Obviously, it'd be more expensive.
Yeah. This is why it's not being used more.
But is it structurally as strong?
Oh yeah. You still have to have the structure is coming from the batten system, which has nothing to do with this. Yeah. Yeah.
So you'd be pinning that to the outside of the back.
Yeah, you would. Yeah. And then you have to go, whoa, is all these insulated products, are they in the deemed to comply? No, they're not. The cladding, the single skin cladding as we know it, is in the deemed to comply, and that's why we can readily use it without it being engineered. So if you're going to use another product like that, you got to get an engineer on board. Yeah. More about that next week when James is in. He'll know all of those things. So for our walls, we can assume that we have an R value from our existing construction, because remember we're buying this house and bringing it in. So from our existing construction, we have 1.49. Well, we need to achieve 1.49. So to be fair, I would never go into a shop and say, can I have an insulation of value 1.49? I'd be saying R 1.5. We need to add an R 1.5 to our insulation. And again, for this one, it would round it to 1.7 for the roof. Is what we need to add. Okay, let's look at our floors. What do we need to do with them? So what do we think our floor is made of in this elevated house that we're buying? Timber. How much timber?
Well, maybe a little bit of concrete and
There might be some CFC in the bathroom, but I think we can assume that our elevated house just has floorboards. Again, they'll be on joist, but we don't count the structure when we're calculating our values. We're just counting the building envelope material, which will be a floor. Most of our elevated houses, if you stand underneath them, you can see the bearers or the floor joists. So they don't tend to have a lining, a ceiling lining for the ground level. So I think we could say our existing R value is just going to be whatever the R value is for a timber floorboard on its own. I know that I've studied lots of elevated houses, and I can look down at the floor and see outside and see daylight coming in. So that's never a good thing for energy efficiency.
before I like should lay a sheeting down before putting the floorboards in, to the extra window ones.
Yeah. You would have to think about doing something like that. Yeah. So insulation needs to have an external and an internal lining. You know, it needs to be in the sandwich. We need to be building the sandwich, and the insulation is going to be the filling. But we need the two slices of bread on either side, you know. Otherwise, our insulation is exposed. So you can have a roof and put your isolation in and drop it down between the battens and allow it to sag. But you'll see it. When you look up, you'll see it, unless you put a lining on your roof. So I think when people talk about the expense of insulation, they're not just counting the cost of the insulation itself. They're often talking about the cost of building the whole sandwich, of providing a cavity in which to put your insulation into. It's also an issue with blockwork walls. So we build with single skin blockwork walls. How do you insulate a single skin blockwork wall? Do you want to look at reflective foil when you're sitting watching TV? Would you like to walk up to your front door and see lovely reflective foil shining at you? There's nowhere to put it. So how do you do it? You have to add another layer of construction. You have to either batten the walls internally, like we just looked at there when I did it on the wall. You could do that. You could put another batten onto the blockwork and put your isolation in, put your insulation in, and put plasterboard on. So then you have to line the whole internal side of the house. And so when people talk about the expense of doing that, they're talking about the expense of the battens and the plasterboard and all of the things that have to go with putting on that second layer of construction. or externally you could have blockwork, and then you could have some sort of what we used to call like a brick veneer on the outside. You have a cavity construction where you've got blockwork and brick veneer maybe, or you could batten out and put metal cladding on the outside as well. But you have to have somewhere, you have to build a sandwich to be able to put the filling of insulation in. Okay, we're going to go and look at floors. There should be something for elevated floors, not on the ground.
No, you get the concession if it's flat on ground, but that's it. That was why it was really hard to get 6 out of 5 stars in Muirhead and things, because they're using the same testing software for 5-star, but there's nothing in there for 4. Obviously, they're flat on ground mostly. There was a couple of elevators, but mostly they're flat on ground, so it wasn't a huge issue.
I might be thinking, sorry, because I did loads of Section J, there is, for the commercial side, you do have to, if you've got a suspended floor, you have to put insulation.
There's nothing in our zone for floors.
Okay, so no requirement for floors in climate zone 1.
And that's the biggest difference between 5 and 6 stars. It's just the
Yeah.
R1.9 and the 5 and the 6 stars, yeah.
So just a note, if you ever, when we talk about the building envelope for insulation, we can talk about this, see this darker line being the envelope, but if you've got a garage, a class 10A associated with that, you can put the envelope around the garage, or you can do this. So that when I talk about the building envelope in terms of insulation, it's about linking up the insulation in the roof with the walls, with the floor, and building an esky. That's the way I like to think about it in Darwin. You're building your esky and you're trying to seal it up. And again, in this one, the option for this one, I believe what they're saying is you can do it like this. You can have your building envelope like this, and then you can put half the insulation value in this wall and half in this. So you kind of double up. So this becomes your part of your envelope by putting half and half. Don't worry about that option for now. Just think about the envelope as building and sealing up your building and joining it all together.
Does that mean the garage itself becomes part of the...
You see, there's no requirement for garages to have it, but you can, there is a requirement for you to seal up the dwelling part of the house. So you can just leave the garage out like they've done here. You can include the garage in and you've still formed a complete envelope for the house. But in this option, what you've done is you've just said, well, if I need an R value for walls of R1.9, I'll put maybe R1 in this wall and R1 in that, and I've achieved R2 by the time the heat gets through the 2 walls.
Do you plan on turning a garage into a bedroom one day?
Mm-hmm. Guess where you should put your envelope? Yeah. So like we touched on last week, I suppose it's becoming a little bit more apparent to you why it's not so easy to convert like a veranda into a dwelling room or a garage into a dwelling room, because A, your slab might not have the damp-proof course underneath. B, your walls might not be insulated around that area. You might have some additional work to do to bring them up to standard as well.
Might be too small.
Yeah. Okay. Yeah.
Yeah. I mean, with the shade here, you wouldn't work out in the driveway or something, would you? Yeah, you'd be in the shade.
Yeah. And like the thing about the garage is that it's probably, well, if you've got walls in your garage, if it's enclosed and not a carport, you've lack of ventilation, lack of insulation, probably no option for air conditioning, and probably no fan. It's probably one of the hottest places you can be. You got fans, yeah. So what the other thing is about insulation. Insulation is only, and I'll go back to this again. Insulation is only for where you've got a temperature difference. Okay, so if outside this house it's 32 degrees, and when we run the aircon inside, we want to run it to a nice 24 degrees. There's an 8-degree temperature difference. So heat only flows through this envelope when there is a temperature difference, okay? No matter, the only way you can have a temperature difference is to have aircon, have mechanical means of changing the temperature. No amount of insulation can make 32 degrees out here turn into 22 degrees there without air conditioning. It just doesn't happen like that. It only talks about the heat, and heat only flows when there's a difference in temperature. Otherwise, it's just equilibrium and they stay exactly the same. Your house will feel marginally hotter always than outside because lack of ventilation and because your house often has heat generating sources, TVs, computers, cooking, you know, all of those things inside. So your house will often feel a bit warmer than outside, and we use aircon to take that out. Where we want the insulation is to stop the hot air infiltrating through the materials of our house, through the building envelope, and quickly. It's all about the speed, the rate of flow. That's what R is, the rate of flow of the heat or cool. The difference in the two types of insulation. Bulk insulation will only to be used when there's a temperature difference, when you're using aircon. Sisolation, slightly different. Why it's so popular up here. Sisolation should be used in all buildings, because whether they're air conditioned or not, because, anyone who want to have a guess? It gets rid of a different kind of heat. Well, condensation is one of them, yeah. You only get condensation as well if there's a temperature difference. You only get condensation with air conditioning. Heat, radiative heat, yes, because when you use reflective foil in your roof, so we've got our lovely, we've got our little battens, and we've done a great job of sagging it between the battens. That's how it should look. Okay, and then we've got our structure and all that going on. Probably have a ceiling somewhere in there too. The heat that comes down from the sun is immediately reflected. Even though that this sits underneath the tin, it's a reflective foil insulation. It works in all instances. It's not about heat difference or temperature difference. It's about reflecting radiant heat. So it has immediate effect. So it should always be used in housing and in sheds and in carports and in garages, anywhere where you're going to have radiant heat, which is everywhere in Darwin. That it just immediately reflects it back. There's a study been done that if you use this on your veranda is 5 degrees cooler than if you don't use it.
Most brands, you'll notice,
haven't got it.
because they're cutting costs.
Yes, because they don't have a sandwich to put it in. They'll put the tin, and then they won't line underneath, and they'll just have exposed eaves, and they don't have anywhere to put the reflective foil. But if you line your veranda and put this in, 5 degrees you'll achieve. Carports the same, warehouses the same, you know, workspaces, people wanting to do, you know.
What's the real difference between the double-sided silver and the blue and silver?
They're usually to do with the manufacturers. Down south they have this huge thing about, I think we have it here too, but I don't hear many builders talking about it, that when you're erecting a roof and you lay this stuff out, so obviously you've got this huge reflective roof, that you can blind the builders and you can blind cars driving up that road. So I think they've got this side just for that reason, and I think after a little while this wears off, and so the reflective foil works, because obviously we want the reflective foil to do the job of reflecting the sun, but we don't want it to blind anyone while they're constructing it. You know why. Okay. I'll take your word for that. I've never had to experience that, but you know, there is some safety issues about the construction of this for that temporary period when it's exposed on the roof before they put the sheeting on.
Can you still get the custom mold? They used to have that lining on the inside. It used to be some sort of zinc lining, so it gave them extra little bit of
Okay.
insulation.
Yeah, no, I don't know. I haven't seen it. I haven't used it.
I got some off-cuts back in the 90s or something. I made the cubby house,
Yeah.
big cubby out there, and I put the insulation in, and I got that tin there, and that's all I had. And I thought, oh, that was pretty cool.
Yeah.
Because
Yeah.
Extra, like,
Extra there.
for a
Yeah.
cubby house.
Yeah. Yeah. Yeah, fantastic for small spaces like that. Like I've certainly done a couple of shade structures for playgrounds, and we've always put this in. You can expose it. You can leave it that you look up and you see the reflective foil. I've done it on projects. It's better to have it than having it. People don't like to see it. They think it looks a bit messy, and then trying to convince a builder that when you can see it, that I still want it to sag. Like they just think that that's going to look like bad workmanship, but there's a reason for that. Yes.
A huge warehouse in Kabul, it was like that. It looked sharp, I thought that it was just really poor work.
Yeah. 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 No, that's a builder that knows what they're doing with it. Yeah. Yeah. Okay. Where am I going to next? Nothing for floors. Oh, we have morning tea. Okay. All right. Let's have a break. Oh my gosh, can't believe we guys just got to morning tea already.
Just whipped on by. It's the same when I do it.
Oh.
The reason why there's none for floor is that because it's obviously concreted.
No, it's because at the 5-star level, they were only worried about the roof and the walls.
Yeah.
So we're going to move on to glazing. As we've said, there's no requirement for the floors.
Yeah, and there's all the cold coming through.
Can't sneak around the house and get a glass of water in the middle of the night, that way you can the whole house up.
So we're going to look at the glazing calculator. So when we think about glazing in terms of energy efficiency, for the deemed to satisfy part of the NCC, looks at basically the area of glass for each orientation of the house. So for each different facade and the direction it's facing in, it wants to know what percentage of that facade have you glazed. Okay? And we do that by means of a glazing calculator, this one. And as you can see, it's been archived because I don't think they're using it anywhere else except the Northern Territory anymore. So the glazing calculator has all different things in it. So let's have a look at one for our house. I'm going to take out the floor plans of the dwelling, the elevated house. We're going to have a look at doing it for that one. So for the purposes of this, I'm going to call it a two-story house because we've already seen how, you know, how it would influence this if we said it was a one-story house, because it would start assuming that we're building on the ground, and it would start assuming that we have a roof right over our windows, which we do. Area, well, let me just check this. So if you click on these little triangles in here, if you're ever using this, it gives you a little cheat sheet bit. So floor type A is if it's in direct contact with the ground, which we're not, so we want to be a type B. A suspended floor, including a timber or steel frame floor or concrete slab. So that's us. So what's our floor area? Do we just for that first floor dwelling area part of the house? Get this thing to go off because I've clicked in there. Here we go.
I think because you're in read only, I'll just save it.
I lose stuff for 1 week, and then I'm like, oh, I need a new calculator, so I go buy another one. And I lose it for 1 week, I'm like, oh, I need to buy another, so now I've got 3 calculators.
Dude.
I know, it's ridiculous, eh? I've got 3 calculators.
Wow. Anybody needs to borrow a calculator?
Yeah, I've got,
Mine can hook you up.
yeah.
Go and cheap.
Isn't it? I've got like 5 rulers.
Dude.
I know, it's bad, huh?
Yeah, the floor area of that entire first floor of the house. And it just needs to be reasonably rough. But let's. So measured within the enclosing walls.
That's only internal, yeah? No verandas or anything.
What was that, Nick?
Just got like super rough.
Yeah. Okay, we'll go with that for now. 100 meters squared. This is asking me for air movement. Doesn't like when I tap S in here for some reason. Okay. So, in the glazing calculator, what it's going to ask us to do, it's going to ask us for the orientation. So, can we go around our floor plan and number our windows? Let me get a floor plan up here. They're already numbered? Okay, so window number 1. Can I have the height of it, please?
The one on the lawn.
Anyone got a height for window number 1 for me? Oh, they're not? No. Right, let's just start nominating some heights here.
There for you
Okay,
without added on.
fantastic. Yeah.
So they're all 1.8, these tall ones.
Yeah.
And then just
I'll just say
600,
600.
and then 900.
So the window number 1 is a bathroom window. Is that right, correct? Would it be 600 by 600? Would that be a fair estimate?
Well, not if you're looking at the picture, though. It's an oblong,
Which one's the laundry?
oblong shape.
Downstairs,
Oh, starting downstairs
on
then.
here. So 600 by 900.
So for the purpose of this, we're just... okay.
By 9 or 12.
Is this on the ground floor?
Yeah.
We're just going to do the floor that is the elevator house. So can we skip the laundry window? What's the next number?
Window 2 is in the dining room.
And is that 1800 high?
Yes,
And the width of that one would be
same.
1.5, is it?
Yeah, it's a bit narrower. Be 1.2, 600, 600, 1.2. So the louver bays are typically 600 millimetres. Any wider than that, you have to have toughened glass. So 2 600s will tell you that it's 1.2 wide, and they're usually 1.8 high, those old windows.
Okay, so when we go along on the glazing calculator, this is how you use it. So basically you want to put your floor area in up there. Air movement, we've just put a capital S for standard air movement. That's just an option that we use. We then go down to here and we list all of the windows and all of their heights and widths, okay? And we also want to tell it the orientation. So we have floor type B. Sorry, back up the top here, we were asked to choose between floor type A. Floor type A was for slab on ground. Floor type B was for anything other than that. And so in floor type B here, we're going to be... So does that window 2, does it face north, south, east, west, northeast, southeast, southwest on our new site? Are you sure? I don't think we've got a true south on this elevation, do we?
No, it's not true, sir.
So what is it? Southwest? I'm going to go with the southwest. Okay, window number 3. You think it's southeast? Let me have a look. Hang on, I'm just going to get the orientation correct first.
Sorry, I'm getting confused. I think I'm confusing myself. That's north.
That's north?
Yeah, that's here, the window. I am just confusing myself.
But north is that way. If I draw north on this, if I turn that, then north is going to be like this. Yeah?
Yeah.
North, south, east, west. Sorry for drawing on your thing. So now, all of this side is northwest. Okay, so up.
Yeah.
So if we draw it like this, we go northwest. We'll draw it over here. Northwest, southeast. I always find it's easier to draw it.
Yeah.
Northeast and southwest. Okay, so southwest elevation, northeast elevation, southeast elevation, northwest elevation.
So it'll be southeast.
So where's window 1?
I mean, window 2 we're doing.
Window 2 would be southeast. Window
Yeah,
1
so-
was what? Or sorry, window 2, yeah.
Yeah.
Southeast.
Yeah.
Southeast, we've just determined. Is everybody happy with that?
I think it's the other way around.
Because the dining room and the kitchen are at the front.
Yeah, we orientated the house around.
Yeah.
So I think the kitchen.
So instead of north being that
This
way,
is your site plan?
yeah, north. So I think we agreed that the bathroom was going to.
Oh, it's going to be on the boundary.
Yeah.
Ah, yes, okay.
And then so that
So if we do like that,
roughly northwest.
then north is going to be by,
Oh yeah, cool. Yeah.
so north is going to be like this.
Yep.
Yep.
Oh, what are we doing?
That's where your north is.
I thought north was that way.
Yeah, but we have to transfer it onto this sheet.
Yeah. So why is that arrow in different position?
So that arrow, so we'll keep this one straight, okay? And so at the moment, the house is like this, okay? And then when I transfer this, sorry, at the moment the house is like this.
Ah.
Yep.
But the arrow's still not.
And there it is. Bathroom's there. So I want this line to be parallel to this one, so I'm going to go like that. So that's why my arrow went like that for north. See, so the arrow changes direction. So if that's north now, and then you orientate to be like that, your arrow has gone from being like that to being like that. It mightn't be quite as
Yeah, I was being
over as that one.
Yeah.
Try not to. East, west, okay? And so then you're going to get your cross ones, and you can write them in where they are, okay? Do you want to copy that one? At the top of your pen. Is everyone happy with the orientation? Despina, have we done it? Did we do it slightly wrong because the bathroom was supposed to be here? I think we've done that slightly wrong on your one.
Oh.
Are you able to flip it round? Yeah, because we mirrored it around.
it actually tells you what the window.
Yeah, it will tell you. That's why I'm asking you to read them out to me. Yeah.
15,
Yeah.
600.
Yeah.
Number 10.
Okay. You happy there, Nick, with your orientation? Yeah.
The rest of the house.
Okay. I'll just get you guys to call them out to me, and I'm just going to pop them in here. All right. So, orientation for window number 2. I'm going to call it northeast. Window number 3.
But the width should be 1.5.
Yeah, but that's got mullions and the window frame, so the windows itself are 6.5 by 1.5.
Right.
So the dimensions for the window width is written on the plans.
So,
Whatever you're going to read off these.
so 1.5.
1.5?
Do you want that better? Because that's actually opening the wall for 1.5.
Yeah, no, that's fine. That's what I would normally put in. Yeah.
Do that then.
What are you saying? It's northeast. No?
Sorry, mate.
It's west.
Yeah, it's west.
It's northwest.
Yep, northwest.
Okay. Window number 3.
Same, exact same one. Same window.
Window number 4.
Same.
Too easy. Once we start getting on a roll with all these things, you pop them in pretty quickly.
Window 5, window 6, same.
All in the same orientation?
Yes, ma'am.
We haven't changed?
No, ma'am.
There's a lot of windows on this elevation. I'm getting worried already.
No.
Call it out. Isn't as high. What room is window 4 in?
Bedroom 3.
Bedroom 3. And how high is it? Oh, the sill level is higher, isn't it? Because it's on the veranda. So let's assume the sill is at 900 and it's 900 high. I don't need to be too. It's more about showing you how to use the calculator than it is about getting precise window measurements. Window number 6.
Same as window 4 and 3 and 2.
And is that northwest as well? Yep. Window 7.
Southeast.
Southeast. We're going on to the southeast elevation. And the height, please.
1.8 as well.
1.8
1.5 wide.
and 1.5. Thank you. Window 8.
Same.
Sorry, that's that bedroom window.
Yep.
If maybe we could have a look at the elevation.
Yep. I did. I had a,
Like it's in on a veranda,
yeah.
so the window could still be the same size as the others.
Because it's hidden down behind the balustrading? Yeah. Okay. All right. Well, I think we will leave it the same as the others. It could have a higher sill because of the veranda as well. But so when you're doing energy efficiency assessments, it's really good to have a window schedule of the house, right? So when I was doing lots of these, I used to refuse to do them until I had a window schedule, or at least until somebody went around and actually looked at the house and told me all the window sizes, because it takes a lot of time to figure them all out. All right. Okay, so I'm on window 9. Okay, so let's assume all those toilet windows are 600 by 600. That would be a pretty standard dimension for a bathroom window. Would you agree?
Yeah, that looks about right.
Yeah, and window 10?
Same. Bathroom.
And it's southeast as well?
Yep.
So obviously it's really important that we're getting our orientations correct. We're going to go put 0.6, 0.6. Window 11?
Southeast, 1.8, 1.5.
And 12?
The one over the kitchen.
Yeah, so we'll assume it's 900 high, because that would be a fairly standard height for a window like that.
And it is 1500 wide.
Whoops. What did I do there? So, okay, so we've 0 windows on the other elevation there, yeah, okay. So 13, or is that it? Oh, we've got one little window on 13. So what orientation am I in there? So if we've got southwest and southeast and northwest, we have to be on a 90-degree axis to that.
Yeah, well they're not though. Like they're not right either. They should be northwest.
Yes. There is a diagram in the NCC which I'll show you that tells you how many degrees you have to be over to default to this. But I'm not going to change in the same glazing calculator. I'm not going to change to just east then. So if we have northeast, isn't it? Oops. Wants to go to east. And we got to say 600 by 600 on this one?
It's 600 wide by...
All right.
Yeah.
Height would be 1.8.
Yeah. And 0.6, let's say. Okay. All right, we've got all our window sizes in. The next part of the glazing calculator is U value. So as opposed to R value, which we spoke about for the roof and the walls, the U value is what we use for glazing. And a U value is the inverse of an R value. So 1 divided by the R gives you the U value. They use U value for glazing. And they also use the SHGC, which is the solar heat. What's the G for? Coefficient, yeah.
What?
No, there's the solar heat
Gain.
something coefficient.
Gain.
Solar heat gain coefficient. Okay. For the glazing. The solar heat gain coefficient is a little bit like what reflective foil is to walls. It's about not letting the radiant heat in. So if we think about windows not letting radiant heat in, we think about tinting. Okay, so the solar heat gain coefficient is about tinting. So this column is, if your window's tinted, you'll have a different solar heat gain coefficient in here. And the U value is about, like the walls, it's about the rate of heat transfer through the glass. So this one will only help you if there is sun shining on the window. This one will help you all of the time, day or night. Easy way to remember it. Any questions on that? Solar heat gain coefficient is it's tinting. It's the tint in the window, okay? So obviously if you've got a window, let's say you're a shop front and you've got a window and you've got, you know, lovely dresses in there all day long and you don't want them to fade because you've got sun coming in that window, you might think about tinting the glass. We get grey tints, we get blue tints, we get green tints, tinting glass. Tinting glass only helps you, it only assists you in not allowing direct sunlight. It reflects more direct sunlight than it allows through the glass. Okay, so your room is darker inside. If you think about a tinted window, your room will be a little bit darker inside. Obviously, that only helps you in terms of heat when there's actually sun outside. It doesn't help you at night time at all. Okay, it doesn't stop heat transferring through the glass. If there's a temperature difference inside and outside, it doesn't stop the rate of flow of heat through the glass. It only stops direct sunlight with radiant heat. So we've got two dishes always to deal with. One is radiant heat, and the other is convection, heat transferring through the material itself. So the solar heat gain coefficient is the coefficient that is equal to the tint of the glass, and the U value is a means of stopping the heat rate of the flow of heat rate through the glass. Can anyone suggest how you might stop that heat rate flowing through glass? Double glazing. Double glazing, perfect. You don't need to tint it. It can be completely clear glass, but it will assist you greatly with the U value of the glass. There's also quite popular in Australia, more so than double glazing, is low E glass, which has a coating put on it, and it's a little bit more expensive, but it's also still single glazing, and that will help you with your U value of your glass if need be. So, sorry. Yeah. Like, it does help you. Like, every layer that you add to a construction will help you, but it also costs you more money. So I would assume that it's a lot cheaper to buy a double glazed unit than it is to put 2 panes of glass side by side. You know, and also with double glazing, what gives you a lot of assistance, a bit like what we saw with the other materials, is the air. There's argon gas, and there's actually air and argon gas trapped between the 2 panes of the double glazing. It's a fully sealed unit. You can get triple glazing, guys, as well. Because they're all those different layers, the layer of glass, the layer of the air trapped in between, each of them is slowing down the rate of heat flow through the glass. So where are we going to find these values from that we need for the total U value? And we're going to go back to our NCC, and I'm going to hope that they pop up in front of me. Here we go. So the NCC for housing gives us, now these figures are really complex, and you can get them from your glazing manufacturer. They're in Viridian Glass, which is quite a popular glass manufacturer in Australia. Has this catalogue, and at the back of that, for every single piece of glass they make, they've got tables, and on that table you will find the U value and you'll find the solar heat gain coefficient. So depending, and so they've got insulated glass units with low E, they've all the different, and they've got all the different tints. They've got clear, grey, green, bronze, so you can look up the data for them. Sharon, you should be able to tell us all about this. Sharon used to work in glazing before this, so you can pass that round and just have a look at the tables on the back of it. So that's where you might go to find those things out. But for the purposes of housing, and for our part-time students who just look at housing, it's quite acceptable to take those values from the NCC. These are guideline values. They're not very well worked out, but they're like an average, and they just use them for the purposes of the calculation. So in our house that we're buying, the elevated house that we're bringing onto site, what do we think? What is the glass, existing glass? Single clear, and we think it's timber frame? Aluminium frame?
You looking at me?
Yeah.
Let me check the plans.
I would assume in Darwin, I've very rarely seen timber frame windows in Darwin. I would be thinking they're aluminium.
Aluminium frame removal.
Yeah, yeah. So our values for the glazing calculator purposes, where's my marker gone? There it is. We're going to use single clear. And we're going to have a U value equal to 7.9 and a solar heat gain coefficient equal to 0.81. That's all we need to know. That's where I'm going to get the values from. They're in the table in the NCC. Back to my glazing calculator. Likely to be, or unlikely to be realistic. Oh my gosh. Oh, 7.9. Yeah, I'm putting the wrong one. That's why.
So we're using 7.9 for single clear off that.
Off the table from the NCC.
3.12.2.1.
Will this let me do this? No. It's not going to play.
That little square on the corner there.
Yeah.
Yeah, I love the trick. It might work or it might not, because sometimes it goes up in value. You can just drag this here. Another copy
Oh,
of
by
the
clicking on the
logo.
first
Yeah.
square. Oh, fantastic.
Love that.
Brilliant. All right.
The only trick I know in Excel, that's the best I've got, people. Everybody go home.
So P and H, what do we think P and H are all about? So we know that shading plays a big role in all of this, so it's about shading. So P, our little triangle up here will tell us, let's go in the way. P is the horizontal distance from the glass face to the shadow casting edge of the projection. If shading is provided by a shading device in accordance with, and that's one of the clauses. So P is the distance of your shadow line out from the glass, and H is the vertical distance from the base of the glazing to the shadow casting edge of the projection. Okay, we're going to look at some diagrams, don't worry. Tables it here. So this is going to tell us about north, south, east and west sectors. So the minute you go across the 22.5 degrees, you're into the northeast sector. See the way that true north is it's basically just divided in not quite half again. All of these sectors are the same distance, though.
They're like 15 degrees increments.
Yeah. Okay. And this is our P and H diagram. Okay. So where we have an elevated house and we've got a overhang, an eaves overhang here. H is, so if the glazing here goes pretty much to the floor, but say if it's not floor level, say we're like up here at 300 mil off floor level, then H is from the base of the glazing. That is not floor level, okay? It's from the base of the glazing up to the height of the projection, the height of the projection that's going to cast the longest shadow, so the furthest piece out to there, okay? Any questions on that?
I'm going to go back to the roofing pitch. You know how we were talking about the 15 and the 45?
Yeah.
This is a double story, obviously.
Mm-hmm.
So to achieve that double story, you're going to have to put that, the veranda thing there to achieve that 45 degree pitch.
Yes, you would have to. But in the glazing calculator, it's really talking about, it wants to calculate what projections you've got over your glass. Yeah. So we're just looking at the roof immediately over each of these windows, and we're going to say how much roof is, what projection we have. Remember, we're just looking at the first floor.
Yeah. Like what you're talking about now is the shadow, yeah.
The shadow, the casting shadow onto the glass. Yeah.
So that's what I mean. Like, it looks like now this is obviously 15.
Yes.
So here's going to be 45.
Yeah. Yeah, maybe. The angle is really just it's for those clauses where you might be an exception of having to do it's more about shading on the walls. This is shading on the glass. It's done a little bit differently. Yeah. So that's talking about if your entire wall is shaded with an angle of 15 degrees, and it's a concession for the walls. Whereas this is just part of the glazing calculator. It's talking about the calculating the shade, the casting shadow on the glass. Yeah. Well, obviously, if you've got a window in that wall, then it's shaded too. But you still have to calculate it out again for the glazing calculator. So, and then it was H and P that we're looking for. Was the other one? And P is just basically from the face of the glass. So do you see the way we are? It's not from the face of the wall. It's not from this line. It's from this line, the face of the glass, to the outermost edge of the casting shadow. So, when I don't know, I take it from the face of the wall. If I knew that it was, a 200 mil blockwork house, then I would assume that my glazing was sitting 100 mil in, so I would minus 100 from the face of the wall. It doesn't always, we have to work here as well. We have to keep moving and get the calculations done, and we could be all there kind of arguing over 20 mil. We have to, we do. So, in a house like this, I'm kind of assuming that the thickness of our walls in this house is probably 100 mil or less. So if we give 50 mil, we'll say that the glazing is sitting in the middle of the wall. So a bit like this. We've got, for instance, let's say, assume that this is the line of our metal cladding, and this is the line of our internal plasterboard, and this whole dimension is 100 mil. Let's say that our glazing is sitting back 50 mil. What distance is our overhang? So we've got a dashed line on plan, and it tells us oh, it doesn't tell us that over. Sorry? 900. I would be assuming that that's 900. So I'm going to say we've got a 900 overhang with no guttering, although we said we might have to provide some. I'm going to allow plus 50 millimeters to allow that the glazing is back. So I'm going to say that P is equal to 950 millimeters. Would you agree? Anyone have any argument for that?
Except for when we modify the overhang at the...
Yeah, oh yeah, we're going to truncate it a little bit.
Yeah.
Over the bathroom.
Over the bathroom, so we're
So when we get to the bathroom window, remind me about that, and we're going to minus that off. Yeah. And H, for our windows that are 1800 high, I would assume that the head height of those is 2 meters 100, which is the standard head height. So then I would be 1800 from 2 meters 100. I would think that they're 300 mil from the finished floor level. Okay, so that means I think the bottom of our window is up 300 here. And what height do I think this is? Do we have a good section through this area of our building at all? Ah, yes. So if I put a ruler down over that section, no, let's show you this one. It looks like, who has a ruler there? You've got one. If you just put a ruler on that and you go from the casting shadow edge of your projection, it looks like to me that it sits maybe 50 mil, let's say it's 100 mil below the window head height. Can everybody see that?
Okay, yeah.
Let me go around. So just if you put a ruler there and go across, does it sit below the window for you? So if you put a ruler here, so we're trying to determine what the height of this edge is.
But we changed it, just forget that.
We will for the bathroom bit though. I'm going to come back to that in a minute for the bathroom. If you get that, if you put the ruler here, you're just trying to determine what the height of this is. We've no real way of doing that at the moment. Normally, guys, when you're designing, you would have the drawing of the section. Sorry, I ran off with your ruler. Well, you probably got 10. So normally we would have this in a drawing or in a model, and we would just measure it. We were just going to go, what height is that projection at? And we would measure up from the finished floor level. So if I'm saying the top of the window head, does everybody see that? So you want to put your ruler here, and you're trying to determine what height this edge is at. This edge here, we need to know this edge for H. So see the way up there where H is measured to? Is that part?
Yeah.
It's where this cast, because this is the edge of the roof that's going to cast the shadow on the window, okay?
The edge to floor.
Yeah, and so H is going to be the sill height of the window, so the base of the window to the line of that projection that's giving it shadow. So from here, the base of the window to the line of that. So I'm going to say, Paul, you're looking confused. Don't want anyone looking confused. Did you see the drawing? So we want to try and determine what height is this point.
Yeah.
Okay? We're going to say it's 2 meters from finished floor level. It looks like it sits just below the window head.
Okay.
Okay? Sharon, are you okay with that? Yeah. Andy?
I don't understand.
So we need to determine what height is this point of the overhang. What height is it? From the finished floor? Actually, for this calculation, we want to decide what height is it from the bottom of the window.
But we can't really determine from that one because we're going to truncate that one. That's the side that we're going to truncate.
Yeah, well, I think that, this one's a bit longer on this side, isn't it?
So yeah, this is the side that we're going to truncate, so we're cutting these spaces up. 300 mil. Cut back.
Yes, yeah, no, we will come to that in a minute. But for a typical window that's
Okay.
not in that bathroom, on the other side of the house, what would the typical height of this be? There's my floor plan gone again. So if we look at the windows of bedroom 1 and 2, let's have a look at them.
Yeah.
You all right there, Andy? So we want to look at a section that goes through there. See, we don't really have a section that goes through there, do we? Okay. Guys, if you have this on your computers, which you will normally have when you're designing, we want to look like as if there's a section through there, and we'll just use this as the typical. So we're going to say that the typical shading projection line in this house is at 2 meters. Okay? The height of the sill height, we've said for a typical window that's 1800 high is going to be 0.3 or 300. So therefore, 1.7 or 1700 is equal to H for the typical windows. Sill level 300 millimeters here. And we're saying that this height is 2 meters from the finished floor level. Slightly, so when our projection comes out, it's slightly below the window head height. We can see that in our elevation. If you look at the elevation, all of your windows are sitting just slightly below the line. That's the section. Have a look at your elevation.
Yep.
Did I leave an elevation on your desk?
No. Oh yeah, is that yours? No, that's mine. Oh no, that's yours.
No, that's mine. Okay, this roof steps up and down a little bit, but we're not going to calculate every single one of them out today because we'll be here forever. So we're just going to say, if you had a section, if you're working in Revit, you can pull a section through every single window and you can measure your projection height quite easily. It's a bit difficult just when we've just got paper and we're trying to scale up it. But H, as you know, we just need to determine the height of this from finished floor level and minus the height of the sill. Let's go back to our calculator. Oh, P, did we work out what P is? We said P is going to be 950, didn't we? Yeah. So, of course, guys, the really quick way to do this is to hire someone to do an energy rating for you. But that might be you. So if people come to you, you can do this deemed to satisfy method of doing it and use the glazing calculator and go through step by step. But of course, if you are accredited, you can be using the software that will give you the star ratings. So that very well might be you. And H, we said, was going to be 1.7. And this is the part of the calculator where you kind of hold your breath. Oh, some of our windows, though, are, so the 1.8 height ones, I'm saying they're all the same. When I get to the bathroom window, can somebody tell me I'm on the bathroom window? What number window was that?
So the bathroom windows, windows 9 and 10. 9 and 10. Window 9 and window 10. Sorry?
ID numbers and window numbers.
Yeah. So the windows, what we're going to say is that our projection is going to be, we're going to truncate this one, aren't we? The bathroom windows. We're going to.
That's not
Oh, this isn't it.
9 and 10. That's 8.
8, yeah. So I'm on window 9 now. Is window 9 the bathroom window? Bathroom window number 9, and we're going to truncate it back to 300 mil. So I'm going to say 0.3 in here, or I'll say 0.35, because I'm allowing the 50 to go to the glazing. My height of H is going to change as well, because the window isn't as deep, it doesn't go down to that. So we've got, if we say our projection on this one's going to be higher, isn't it? So if we say the line of P on this one, if we truncate it back to 300, it's probably going to be something more like 2 meters 300 high. And our sill level for a 600 window, so 2 meters 100 minus 600 is 1500 high for our sill level. So I'm going to have 800 mil for my H. Does everybody understand where H is coming from? If you don't, you need to tell me now. The 2.3 is the height of the projection. So let me show you. So the height of this, I'm just saying if we chop it back to be only 300 mil, it rises with the roof line. So it's a bit of an assumed one, but we said that where the roof line comes out 900 mil, we said that that's at 2 meters. And if we cut it back to 300, I'm just saying it's rising accordingly. So I've assumed it's 2.3. I haven't measured it because I have nothing to measure it on right at this moment in time. But again, if you're modelling, you will be able to measure that more accurately.
Wouldn't we be taking the edge, the underside?
Do you mean down here?
Yeah, right there, yeah.
No, you take to the edge that's going to cast the shadow. So if you think of a shadow coming down, it's going to catch this edge first.
We haven't got a horizontal underneath.
Yeah.
Now it's overhang.
You generally take to the edge of your gutter.
Yeah, so you got a gutter on this.
Well, I don't really know if I've got a gutter. I don't think I do. We have to gutter it, yeah. Yeah. Let's not get too wrapped up in exactly what height that projection's at and whether it has got a gutter and all of those things. If you were doing this in reality, yes, you do need to take all those things into consideration, but hopefully in those scenarios you would have a detailed drawing in front of you that you'll be just able to measure off. But you're really thinking about the outermost point of the shading projection. And you kind of hope it's not stepped like that. I don't know why they had to draw it like that. Yeah.
That's the bath, because that's the bathroom one that we're doing.
Yeah.
It will have a gutter.
It will have a gutter. Yes, it will.
It will extend.
Yeah.
The main measurements is page 10.
Sorry?
They're the main measurements that we have to know.
Yes, yes. And these are all in the NCC. The main measurements are the H. So remember, it's not from the floor, it's from the sill line, and the P, and it's measured up as far as the line of projection. And P is the line of projection from the face of the glazing. And you can always refer back to this diagram. It will tell you what they are. It's in the NCC. All right, back to here. Yes? Window 10, is that a bathroom window too?
Yes, same.
So that's going to be the same. Were you going to ask something there, Juan? Did you want to ask something?
Oh, no.
No.
So H, because the bathroom windows kind of sit high, is that why you got the value of 80 there?
Yes, because for 800 here, what I said was the sill height comes right up. Because it's only 600 deep, that window. So I took 600 from average window height of 2 meters 100. Yeah. And that's where I got my 1500 sill height. I had to take the sill height from the height of the projection, and that gave me 800. Okay, so we're back to fairly standard windows here. I'm going to use the standard measurements. Of course, if you're doing this in reality, you have to look for every single window. And it is a little bit of a time-consuming exercise to do the glazing calculator. So this one's a bit short. It's let's say, so this one is a funnier little window here, number 13. It's on the northeast elevation. What happens with our shade on the northeast elevation? It's in the dining room. This window, it's window 13 in the dining room. Yeah.
Quite narrow.
But what's different about it? It's sitting on the end elevation, isn't it? So it doesn't have any projection overhang. So look at your roof line. On plan, look at your roof line and look what it's doing. In elevation, this is this window here. So it's on the apex. Yeah.
The window 12 also sits higher because it's a kitchen window.
It's a kitchen window. Oh, okay. So which one's that? 12.
Yeah.
Oh yeah. So we got the height. So this was wrong, isn't it? H is wrong.
Yeah.
H minus 90. Minus 90 is 0.8 again. Yeah. Okay, so window 13. What do you think we're doing here? Do we have any projection at all? We probably have a projection of 100 mil. I'll take that. And what about H? For this one, I would literally put my scale rule on the base of the sill and I would measure up to the center point of the window up to wherever the projection height is on my elevation. That is really the only way to work it out. So the window itself is 1800 high, and I would say we probably go another 400 mil above that. So I think H is about 2.2. Anyone want to argue with that? 2.1? I'll take 2.1. That's fine with me.
Say that they put an awning there.
Yeah.
The awning.
Yes, absolutely. Yeah. Now.
It's always good to do an awning for the whole wall rather than just the window.
Yeah. If we're doing an awning that's just for the window, the rule is that the awning has to, whatever it projects out, so say your awning projects out 600 millimeters, it must project 600 millimeters on either side of the window too. Okay? Does everybody get that rule? So you can't, there's lots of apartment buildings in Downers, so we should take a photograph of this one day. And they've got like these big block walls. Yeah. And you've got little windows. This is just a very basic drawing. And the shade does this. And when the sun comes from here, often the casting shadow for that shade is like this. Okay? So half the window's not in shade anyway. And that's for most of the day. And one of these days I'm going to take a picture of one of those walls of those big apartment blocks and all of this tiny little shades they've got over the windows, and they're not actually shading anything. So the rule in the NCC is that if this shade is projecting out this way, 600 millimeters, it's also got to go 600 millimeters this side and this side of the window. So that has to be the width of your shade. It has to go further than the sides of the window. So if it projects out 3 meters out the front, you got to go 3 meters either side. If it projects 600 out the front, you got to go 600 either side. Yeah. Yes, the sun does move. Okay, so,
And the earth is round.
calculator outcomes are hidden until input issues are resolved. Oh. Let's see where else they want me to put anything. Usually at this point when you put that very last figure in, this side lights up either green or red.
Area.
I've got it in here.
No, the area for each window.
Oh, it should just calculate it. Maybe not.
Width and the height.
All right, who's got the calculator? Let's put the areas in. 1.8 by 1.5.
2.7.
No. What did we get? Yeah, will it make a difference? Sure will. Whatever climate zone we're in. Alrighty. So this is what happens to the glazing calculator. And we really wanted a big green tick down here, but we got a big red X instead. So this building doesn't comply. Where doesn't it comply? Sorry? The area hasn't been filled in, or the area's in? Or the windows areas. It's fine because it's got the height and width. It already knows. It already knows. This is already in the body of it. You can either enter height and width or area. But generally on plans we have the information for height and width, and I don't bother working at the areas. You don't need to do that. So a couple of things you can start thinking of doing. You can start thinking of tinting your windows. That might help. So we passed on conductance. Do you see this? We didn't pass on solar heat gain. And what do you need to do to pass on solar heat gain? No, that's the other one. That's the conductance. If we failed on this one, on the solar heat gain, you could either shade your windows better, or you can tint the windows. Yeah. You can tint the windows. If we start.
It was common in the old style elevated houses for the lower third of blades to not be glass, but to be timber or steel. So it just, you can close them then and the light can't get through, particularly lower down on the projection because the shade doesn't necessarily reach that far. So the lower third of the glass is replaced with timber or cedar or metal. Yeah, the conductance goes up.
Where the windows sit, though.
I've actually.
It's got the height and it's got the shade of the window. It doesn't really matter. It knows the orientation, but it doesn't know where on that wall it is. And that's fine. It doesn't need to know that.
Where does that have the sill height?
In the H calculation, we took account of the sill height.
We just told it it's 1.7.
Yeah, because that's
not saying where it's going. That's 1.7 high window. That could be right down here or.
It can, but it does. It is in relation to the height of the shade. So wherever the shade line is coming down, it's got the sill height to know whether or not it's shaded or not down at the base of the window. Like Lisa said, sometimes the base of the window is where it gets the most direct light because it's out of the casting shadow of the projection. But the H calculation, the H will tell it that. It tells it where the window is in relation to the line of shadow.
See, this is, I've lived in houses with these three bottom are metal. And I thought there was a design error, so I took out all those three, and then I took all the levers from the bathroom and pushed them all around. Didn't even think of it. I'm like, who the hell does that? It's stupid. So I took all the windows, and then
So if it's a solid louver, is it a wall or a window?
Yeah, it's a window.
Is it a window?
So yeah, I just took all the bottom, all those bottom three, and then I was like replaced it with the bathroom ones.
It's very hard to know what to do with those solid louvers in this calculation. Yeah. I tend to treat it as a window. Yeah. With a solar heat gain coefficient of completely opaque. Yeah. But you can't treat it as a wall because how does that louver panel, even though it's solid, how do you get an R value for it? And if it's compliant, it's part of it. If you're treating it as a wall, it has to have the compliant R value.
Oh, okay.
Yeah, so treat it as a window. Exactly. It's not a wall either. It's not acting as a wall. It's not got an R value to protect you from the heat. Yeah, and the heat's still coming through it. Yeah. Yes. So that's how you do the glazing calculator. I would suggest that if we go back to here. Where did I get those values for my solar heat gain coefficient? And just looking for that little table again. So that's double glazed, single glazed aluminium, tinted single. If we said when we move our house, we've got to replace all the glass with tinted glass. And our solar heat gain coefficient is going to go from 0.81 to 0.65.
Project just got really expensive.
All of this changes to 0.65.
The louvers might all break on a travelling distance.
No,
anyway.
isn't it the column before where it says 0.1?
Whoops, this is, what did I change that from now? 0.95.
on the right.
Yeah, that's it.
Yeah, once you get the little plus. Click away, because you're in the, you've got, click away for a sec. Click somewhere else, and then go back. And then just hover on the right hand. Yeah, and drag. There you go.
Woohoo, new skill today.
Yeah.
Oh, we didn't make it, did we?
Did it change anything?
It changed the figures, yeah, but we're still not there. See, we're at 112%. We have to get this down to 100% or less. If you're at 112, you've gone over. So the other thing you would really be thinking about doing is putting some extra awnings over the windows to get some shade.
If we brought the bottom,
the sill heights up?
up?
Yeah, absolutely. Sill heights up will make a huge difference, yeah. Yeah, so to bring sill heights up, where we've got that is in H. So say we, to do this now, I'd have to change the height of the windows and the heights of H. Well, if we bring them all up, it's a lot of work to go through and start editing it.
What you're probably looking at is trying to compensate with extra insulation in the walls to compensate from the solar
you
out
can't,
of the window.
would deem to satisfy, you're not allowed to do that.
Oh no, I'm talking about the 5-star.
Yeah. So the joy of the 5-star ratings, because it's a performance solution, it looks at the whole house. So what you can do is say, I'll put extra insulation in my roof, and my windows are, a weaker part, and they're non-compliant, but I'll put extra in the roof, and we balance it off that way, because it's a holistic look at the whole house. Whereas with the deem to satisfy, you have to comply with the roof, you have to comply with the walls, and you have to comply with the glazing, or each in their own individual right. Glazing.
They're going to replace all this movements here with like this solid glass.
No, you can't do passive cooling with solid glass.
No.
They want that.
Yeah.
Yeah. No, we'd be
Tinted glass is a good idea.
Okay.
Very good idea.
tinting the glass. Yeah. We could go back to that.
It's likely that the glass in the building that we're receiving is quite old, so it'll be brittle. Glass is actually a liquid, even though it doesn't look like one. So over time, it actually narrows out. The gravity will actually change the shape of the window. Yeah. Old glass does.
Yeah, it does. New scientists, like 3 months ago.
Oh yeah.
Proven back science, not building.
So I took, those old cottage windows and doors that had just tiny little panes, because glass could only be made really small. A long time ago, you couldn't make big sheets of float glass like they can now. And I had a little cottage door, and we broke the glass. And we took it out, and it was so thin at the top, and it was definitely wider at the bottom. I mean, it was old glass. I mean, we're talking like 150 old.
They've done the same thing. They worked it out that it's basically because it was thicker, that was the way they laid them. There's plenty of stained glass windows in churches that are thicker at the top. So it's not right. That's just this recent article that says.
Yeah, right. Oh, well, there you go. Anyway, so the glass itself is probably non-compliant thickness-wise as well, apart from being brittle and not necessarily being liquid anymore. But it'll probably be non-compliant depending on the width. So I mentioned before that wider than 600 millimetre louver blades need to be made of toughened glass. So we're probably going to be expected to upgrade the louvers anyway. So there's an opportunity there to tint the glass. If you want to make a note for your report for that, it's a dual hit then. We'll be bringing it up to code. It'll need to be toughened if it's greater than 600 millimetres. Standard louver bays aren't greater than 600 millimetres. They're about 594 wide, the actual glass, and then you get the frame and things. But we might well have slightly wider louver bays. So we'll have to source some glass that will fit.
So notes for a report from this morning, just what Lisa said about the glass. We're going to tint the glass. I even go so far as to say we're going to provide additional awnings over windows.
No, I don't think, you probably won't, but we'll probably go for the alternative solution and beef up the insulation to compensate for the gain. And maybe look at timber louvers for the lower third.
Yeah.
It's not going to.
Yeah, you could say that. You could put timber louvers in the lower third of each of the windows, and that would
nice
probably
look as well. I wouldn't go for the steel because the reduction of heat through the steel is quite great regardless, even though it creates shade when you're closed.
The other calculations we looked at this morning, your roof, your required R value is 2.7. We're going to use a light coloured roof material, and we're going to reduce the requirement to be 2.2 R value required. Our construction, we can assume from the NCC, gives us an R value of 0.53. So we need to add insulation to our roof. This needs to be in your report. You need to add insulation in your roof. That equates to 1.67. You can round that up to 1.7 R. Your insulation must give you an R value of 1.7, what you're going to add in the roof. But I need you to have all of that calculation, and I need you to understand it. This is what the NCC says you're required, 2.7. It tells you can get a concession for using a light-coloured roof. We've agreed to do that. That's giving us a concession of 0.5 of an R value. That gives us a total 2.2 R value now required. Our construction made up 0.53 of an R value. That gives us the remainder 1.67 R value that we are required to provide by means of insulation into the roof construction. For the walls, required R value is 1.9. We've looked at the actual construction. Remember, we took out the custom colour bond and the wall stud frame and the plasterboard. That gave us a total R value of 0.41. If we take the 0.41 from what we were required to provide, the total 1.90. The remaining R is R 1.49. We can round that up to R 1.5. You are required to provide insulation to the value of R 1.5 in your walls.
Finding insulation at such a low R value is quite difficult these days. The R value of insulation is quite high as a basic level, so you won't have any problem finding a product to meet that or higher. R3 easily. So
just remember too, if you're providing bulk insulation, you are restricted by the depth of your cavity. Okay, so you want to, if you get a blanket that's required to be 200 mil thick, and you want to squeeze it into a 75 mil stud, you're compromising the R value of the insulation. You might as well go and buy the insulation that is 75 mil thick, because you're not getting anything extra for the extra money you'll spend on the 200 mil thick one if you then squash it in. Pointless exercise. Waste of money. Just buy to suit your cavity and buy the quality insulation that will give you the R value that you are required to provide. All right. If you make notes about the roof, walls and the glazing, and make sure you've got those notes down for your report, we'll leave it there for now. Actually, I might just quickly run through building ceiling while you're writing down those notes. I've got like 3 minutes. I thought I was a bit closer. Building ceiling is a whole other section. Remember in the beginning we looked at the sections of this part of the NCC. I'll pop back up there. So we had building fabric, which is the walls and the roofs and the floors. External glazing, which we just went through, and now we're on the third part, building ceiling, and we'll have to look at air movement in the afternoon. I can't believe I didn't get all this done in the morning, but it is quite complex. Another bit. So building ceiling is really talking about what we used to call caulking in the old days. It talks about how you seal up your buildings. So there's a little bit part there on flues and chimneys, which I'm not even going to go there. There's a little bit on sealing up roof lights. External doors and windows. A seal to restrict air infiltration must be fitted to the edge of an external door, openable window and other such opening when serving a conditioned space. How many of you have doors at home that you can see the light coming in underneath? That is not compliant. If you've got louver windows, that is glass on glass, that is not compliant. You need to have a rubber strip on the edge of your glass. So you need to be able to seal, yes, you need to be able to seal doors and windows. Sliding windows, they need to be able to, close enough that there's no gaps around the edges. If you've got cobwebs in your windows, it means the spiders are getting in. It also means that your cold air is getting out. In our climate zone 1, it's when serving a conditioned space. In climate zones 4, 6, 7 and 8, it's when serving a habitable room. Slight difference there. The following need not comply with an external louver door, louver window or other such opening. So we do have concessions for louver windows at the moment. In the next step up of the energy efficiencies, that disappears. and a window complying with the maximum air infiltration rate as specified of AS 2047, and as we know is an Australian standard which talks all about the sealing of windows and doors. The easiest way for you to find that information is to ask the window manufacturer, does he comply with AS 2047, and what's the sealability of the windows and doors. Exhaust fans, another area where we lose a lot of air in our buildings. An exhaust fan must be fitted with a sealing device such as a self-closing damper filter or the like when serving a conditioned space. So if you've got your kitchen exhaust fan and it just has a big hole that goes out to the outside, that's not compliant. It needs to have a damper that when it's not in use, it's completely sealed up when you just don't have air leakage at that part of your house. So the constructions of roofs, walls and floors. Roofs, external walls, external floors and any such openings such as windows, doors or the like must be constructed to minimise air leakage in accordance with B, when forming part of the external fabric of an air-conditioned space. And B, then construction required must be to enclose internal lining systems that are close fitted at the ceiling, walls and floor junctions. So obviously where your ceiling meets the wall and where your floor meets the wall, we really should be looking at, and we use coving around the top. This is one of the methods, or skirting boards at the bottom. These are some of the methods we use to really seal up our buildings, to make sure there's no air gap in between where the ceiling is meeting the wall, and then that air goes up into the roof space and that leaks out through, some sort of gap that has been filled in the roof space. By using some sort of a strip of sealant around the edge. But this is about good workmanship. This is about on-site care being taken not to leave gaps in between different parts of the construction. So how I've dealt with this previously is like a standard note on my drawings. If somebody sent me a set of drawings for energy efficiency, I would send them back with a standard note written on them about sealing, and it would be literally taken straight out of the NCC. You must comply with this clause of the NCC in your standard detailing and in your workmanship on site. Evaporative coolers, we don't use them a whole lot up here because they're not great in humidity area. However, they are used quite a lot in Alice Springs and as we get down towards more the desert areas, and so they too must be fitted with a self-closing damper. And then we're on to air movement, which we'll do after lunch. But that was just that third chapter of building ceiling is just about those fitting self-closing dampers and.
There's fan things that supposed to suck out the heat out of your ceiling space.
Whirly birds.
Anymore.
So when we looked at roofs, we kind of skipped over this bit. So in the NCC assumes that you're going to provide insulation at ceiling level. Now I don't know how many of you remember a couple of years ago there was the fall-backed insulation scandal, and a couple of electricians got electrocuted in roof spaces, and unfortunately that made the whole industry turn away from insulating at ceiling level because there's a lot of electrics go on at that level too, and a lot of our builders have gone to providing bulk insulation, so a blanket insulation, and they'll lap it over the battens and they're providing it at roof level. Let me draw my famous diagram. Has everybody taken these notes down? Because I was going to leave them there for lunchtime. Maybe I'll just fit this little diagram in here somewhere. I just want to leave them there in case somebody wants to catch up at lunchtime. So if you've got, this is going to be a small drawing, your house with the roof, and you have your insulation for the roof. Remember I said we showed that diagram, the roof involves the ceiling as well. So you've got a ceiling in here and you've provided your insulation here. So your building envelope is there. Okay? It is a really great idea to then ventilate this roof space because it gets rid of any additional heat in the roof space. If your builder decides that he's not going to insulate at the ceiling and he provides his building envelope there, and the insulation forms part of the roof, and that's your envelope, and you've insulated all the way around, and then you run air through that, guess what you've just done? You've just left the lid off your esky. You've just opened up the roof, and you have allowed hot air to come inside your building envelope, the part that you were trying to insulate and keep cool. So the NCC gives you, remember it gave you a 0.5 concession for the light-coloured cladding on the roof. It also gives you a 0.5 concession for ventilating your roof space, but it is assuming that you're doing that while insulating at ceiling level. And the reason I didn't allow you to go for that concession was because hardly anyone ever insulates at ceiling level. So you must do the two together. So all around Darwin, there are lots of whirlybirds on lots of roofs, and the roof is also insulated. And they might as well go camping for the weekend and just open that lid on the escalator and wonder why the ice is melting.
So that example that I gave before about those flats putting up the road that have put the sunlight in and the whirlybirds, unless they put that in the ceiling,
yeah,
it actually opened up.
Yeah. Yeah.
Losing.
Yeah.
So, which one's better? Insulating the ceiling, having a bit of ventilation as well, and
If you've got a flat ceiling and it's a conditioned space,
Yeah,
the
I would. Yeah. If
you don't have a flat ceiling, if you have, say, a pitched ceiling, then you would have to put the insulation under the roof. But if you didn't have a ceiling,
I personally, I would like to see insulation more at ceiling level. What it does is it makes this area smaller. You have a smaller area to condition. Like, you know, when we think about our ceilings in our living room, when we're sitting at home watching TV, watching a lovely movie, and the aircon's on, feels lovely. That plasterboard ceiling that you're looking at on your ceiling is only, where's my sample, this thick. The heat is going through it. There's no insulation in it. If you put insulation in the ceiling, then you're all nicely snuggled up. But if you have your insulation up at the roof level, anything that's happening in that roof space is happening in your air-conditioned space. That roof space is part of your air-conditioned space. The air-conditioned space is wherever the insulation is around. Yeah. Make sure you've got the ceiling, and then you can put your whirlybird up here. You can do your ventilating your roof space, move lots of air up there. It's a great thing to do in the tropics, but it's just not a great thing to do if you're going to put your insulation up at roof level as well. Yeah. No, ventilation's to remove any hot air out of your roof space. The problem is if your roof space is included in your air-conditioned space, then you're moving out the air-conditioned air as well. The R value is calculated with the roof and the ceiling together. The R value, when you calculate the R value for roof, it's from here to here. Everything in between includes the ceiling. It's called a fly roof. If you've got a fly roof over and it's out open to the outdoor air, well then you can put your insulation wherever you want in your main roof, and then a fly roof is just there for shade. It's a great idea. But no R value. No. But if you were doing an R value calculation, you had a fly roof, you would include it because it gives you lots of benefit.
My house was designed in the 1980, 82. It wasn't designed with air conditioning.
Yeah.
It's not insulated in the ceiling, but it's got open eaves all the way around.
Yeah, it's a ventilated roof space, yeah.
Ventilated through.
Yeah. But I bet you somewhere along the way somebody put an air conditioner in it.
Yeah, in the bedroom.
Yeah. Oh, in the bedroom, okay. Yeah. Well, think about insulating the ceiling of your bedroom.
Well, yeah, I am. I always have done it, but I've got to rent it out, so no problem. But one advantage is it's one better block higher in height.
Yeah.
And the difference between walking into that and the house which is next door, which is one better block lower, without the air conditioning, they air condition their place all the time, as the land room in this one, the air conditioner, you don't need to air condition it as much.
there might be lots of contributing factors to that though.
Yeah, well,
shade, colours,
the most obvious
ventilation,
one
adjacent obstacles, there's all sorts.
Yeah.
Well, that was the most obvious one.
I mean, having room for the hot air to go does make a difference.
Yeah.
Yeah.
Going to lunch.
All right, we'll leave it there for lunch. We'll see you back at 10 past, and we'll continue on from there.
Very interesting.
Just pause.
Sorry.
Because you want to finish the energy efficiency
Okay.
before the recording finishes.
Okay, so we're back for the afternoon, and we're just going to look at the fourth part to the part 3.12 of the National Construction Code Volume 2 for Class 1 housing, and we're looking at ventilation. So this section is all about air movement and ventilation. So as we know, there's a couple of ways to keep yourself cool. One of them is actually bringing the temperature down. We know from this morning's session the only way we can bring the temperature down is by applying mechanical cooling, air conditioning. However, the other way that we can feel cooler, it doesn't actually bring the temperature down, but we feel cooler as human beings if we have lots of air movement. Why that works best, especially in a tropical environment where we've got humidity. When we've got high humidity, when it's hot, we sweat. Why the humidity makes you feel hotter is because the sweat doesn't evaporate off your skin. Air movement will get the sweat to evaporate off your skin a lot faster. As you know, when you stand in the breeze, it doesn't mean that it's still not 33 degrees, it's still 33 degrees, but the breeze is making you feel cool because you've got evaporation going on around your body. So within our houses then, we can have breezes coming through because we've got lots of openable windows, and we can have natural breezes coming through, but also we can have a mechanically assisted means of that by means of a ceiling fan. So it's the other essential way that we get air movement in our buildings. So for Climate Zone 1, we've established we're in Climate Zone 1.
Drastically changed.
They have? Yeah. They will have in the latest copy of the NCC. Just for your benefit, this morning we looked at the NCC that's still the regulation in the Northern Territory is the 2009 version. So we're looking at 2009 for this on the screen. Excuse me. So this table on air movement, we're looking at Climate Zone 1. So it says up the top there, the minimum total ventilation opening area per habitable room. So in other words, the percentage of the area of the floor of the habitable room. So what we want to do is we want to get the floor area and the area of openable window space. That is not the same as the area of the window. For a slider, it's 40% of the area of the window because it's the actual opening component. For a louver, we can assume that's 90% because we minus off the frame and that tiny piece of glass that still restricts air movement. And so without a ceiling fan or evaporative cooler, we want that figure to be a minimum of 15%. But if we have the fan-assisted air movement, we can reduce that further to 12.5% of the floor area. It needs to be an openable area in the window. Let me just have a quick look through. So it says air movement A. Air movement must be provided to habitable rooms in accordance with that table. B. Air movement required may be provided through an opening from an adjoining room. If the adjoining room is not a sanitary compartment, so you can't borrow air from a wet area, not a good idea. The opening between the adjoining room and the habitable room complies with the table, as if the ventilation opening to the habitable room or portion thereof, if some of the ventilation is provided from another source. So really this, again, it's just talking about borrowing air from one room to the other. So if you've got one room that's got a really big window and it's supplying way more than the 15% allowed, let's say we've got an opening that's 50% of the room area, big bifold doors or something like that, and then we've got an inner room off that room. It still has to have either door openings, and we can borrow some of that ventilation. If one room has excessive amounts of ventilation, we can borrow and let the breeze come through the two rooms. And the ventilation opening to the adjoining room complies with the table for the total area of the floor of the adjoining room and the proportion of the habitable room that is ventilated from the adjoining room. So obviously that opening needs to be big enough to cover both rooms. It doesn't apply to Region D. The requirements of A do not apply to buildings in Region D, severe cyclone tropical areas. That's us. provided that the external walls are shaded with a veranda, the external walls achieve the R 2.5 and the roof achieves R 1.5. I've never applied this, even though we are in a tropical cyclone area. We're in Region C. We're not in a Region D. Region D is over around the west coast of Australia. It's actually a higher cyclone rating than we are. So this doesn't apply to us. So we do need to comply with this table. We'll just continue down through the clauses here. The ventilation opening in climate zones 1, 2, 3, 4, 5. We're climate zone 1. The total ventilation opening required by the table, the habitable room must be connected by a breeze path, complying with B, to another ventilation opening in another room or space. So you can do cross-flow ventilation through doorways in different rooms across your house. So there must be a path of air movement. Why we want 2 ventilation openings, because we know that in Darwin, even if you've got one room with just one ventilation opening, it doesn't mean that the breeze is going to come through that window. What we want to do is draw it through the window, and that we do that by having other ventilation openings on the opposite side of the house, so we get cross-flow ventilation. And that's all that's telling us. They must be connected by a breeze path. Be provided by a minimum of 2 ventilation openings located in the same habitable room. Each ventilation opening having an area of not less than 25% of the total area required. And the breeze path must pass through not more than 2 openings in the internal walls, with each opening having an area of not less than 1.5 meters squared, which is a doorway. And have a distance along the breeze path between ventilation openings of not more than 20 meters. So it's just telling you what are the constraints for that breeze path. In general, the 20 meters is quite generous. Most people's houses are not much, won't be much wider than that or longer than that, and we can get so we'll just read the explanatory information. Ventilation openings should be designed to allow the interior of the building to take full advantage of any natural breeze. Careful consideration should be given to the type and location of openings to ensure optimum effect is achieved and that internal dead air pockets are avoided. Any opening may serve more than one breeze path, so you can link them all up. 2 openings that are stated in B1 as the limit of the number of openings permitted in a breeze path. These are typically doorways. Larger openings, such as those adjoining a lounge and dining area in the same space, are unlikely to restrict air movement significantly. So just a single leaf doorway is enough to be on the path of the breezeway. Ceiling fans, what do they have to be? A ceiling fan or evaporative cooler, which we said are not used a whole lot in Darwin. Evaporative cooling might work a little bit when we've got like really low humidity in the dry season, but it wouldn't work very well in the wet season, because evaporative cooling actually adds moisture to the air, and in a tropical location where you've already got high humidity, you really don't want to do that. That's not going to make you feel cooler. But a ceiling fan will. So the ceiling fan must be permanently fixed, have a speed controller, and have a blade rotation of not less than 900 millimeters diameter. So that's the diameter of the ceiling fan. Okay, we generally use 900ths or 1200ths in Darwin. And that's it. So, do we have a drawing of a cross-flow ventilation? No. Okay. So, for the calculation for this, we need to work out the floor area of each of our rooms. And then we're going to work out the area of the opening for each of the windows. So I'm going to rub this off. Has everybody taken a note of this? Josh, you might want to take a picture of that. I'll just rub that out because that doesn't make sense in the middle there. These were our calculations for our R values. All right. We're going to go room by room. Is your orientation thing finished?
Yeah, it was cancelled.
Oh,
yeah.
I was wondering. Imagine that. Okay, we're gonna.
Bring the floor plan up on the screen.
Oh, yeah, that'd be great, actually. Did you do kitchen, living, dining all as one room in this? Yeah. So remember, we're just doing this for the habitable rooms. That's the list of the habitable rooms on the board there. It's tall enough.
Finished using a markup concept, I can bring the height back down if you want.
Ah, that's all right. It's okay, we'll use that as well.
Think tall.
Yeah, no, it's good for me to stretch. Do we have an area for the kitchen, living, dining? Anyone calculated that out yet? No, inside the walls. So room area, we would just go inside the walls of that room.
You can count the kitchen bit though.
Yeah, you can count the kitchen bit.
Yeah.
Who's got the calculator? 6.3 by 6.2. Yeah. No, but they don't have to be too absolutely precise, but you know.
The kitchen's only 34 by 27.
37 meters squared. I'm going to take that. It's fine. I haven't done the calculation myself, so we don't have this anywhere, do we?
Not that I recall.
Is it you've done before? Just calculated it out? Anyone verify that? I'm on a 42 here.
Well, if you take into account
The entrance door, yeah.
45 square meters,
Got 42, I've got a 37, I've got a 42. I just need two answers the same. I've got a 37 for the kitchen, living, dining. Let's say, for the purposes of the calculation, it's 40 meters squared. Okay? That seems to be a bit in the middle. Okay. Bedroom 1. So bedroom 1, we've got 4.5 by 2.9. Can I use your calculator?
Yep.
$13. Bedroom 2. Anyone got that one worked out? 2.8. So you better read in the dimensions than actually scaling off the drawings here, folks, by 3.8. Oh, sorry, 3.3. Got that wrong. Sure, cancelled. Oh, yeah. 3.3 by 2.9. Oh, 2.8. So 9.2 I've got for bedroom 2. I'm going to leave it to 9 for the ease of calculation. And bedroom 3. It's a bit hard to tell whether the linen and the robe is in the bedroom or in the living room, isn't it? Let's just take it that they're in the bedroom, so that would be 3.4 by 3.3. Just that line, but I don't want to have to calculate that. Yeah, I can imagine.
That way, and then they go that way.
Yeah, that way. I'm not going to calculate all that out there. Oh. Yeah, we're not going to be too worried about that today, because we do need to keep going. Yes, because I took the built-ins to be part of that room, so I've added 600 to the 2.8 for the width of bedroom 3, so that gives me 3.4. 3.4 by 3.3. Yeah, I just added them in this one. Okay, so those are the areas of the rooms. Now the window areas. Let's look. So in the living area, we've got window 11, 12, 13, 2 and 3. Can everybody see that? So window 2. Why is my marker not writing for me on one side? Window 3, window 11, and window 12, and window 13. And I'm going to be really clever, and I'm going to go back to our glazing calculator, which gives me all of, it doesn't give me all the areas, but it kind of does. So window 2, what I did was I took all these robes in as part of bedroom 3.
Ah, right.
So I added that 600. Yeah. I've got the extra 2 meters there. So window 2 is an area of 2.7. Window 3 is going to be the same. Can everybody see that on the glazing calculator? Window 11 is going to be the same, 2.7. These are all our nice big windows. Window 12 is different. 1.35, thank you. And window 13 is 1.08. We're going to add all that up and we're going to get 90% of it. Somebody do that on a calculator for me. So why are we getting the 90%? Because we're saying they're all louvered windows. And in louvered windows, the NCC estimates that you get 90% ventilation opening from a louver window. I know that because I've done lots of energy efficiency calculations, and in the software for the modelling, it allows the louver window to be 90%. No, this isn't thinking about the 15% just yet. All we're doing is adding up all the window areas together.
Is that it? 10.5.
Yeah.
That's the total, not 90%. That's just the total.
Okay.
That's the total. So that's so of window space we've got 10.53 equals. So that is how much ventilation area we have from those windows to the living area. We get that? So we've got a floor area of 40 metres squared for the kitchen, living, dining, and we've got a ventilation opening area of 9.47 metres squared. The window area is the 10.53, and then we've said what's 90% of that, because that's the openable area of the louvers, and we've come up with a figure of 9.47 metres squared. Any questions on that before we move on? It's just simply a calculation. You're just getting the areas against each other. So, $40 meters squared is equal to 100%. If 9.47 meters is equal to what percentage of that room? Cross multiply. So we've got 947 divided by 40. 947 divided by 40, anyone?
Almost 24.
No.
23.6.
0.6%. Oh, I don't want to bring it over in the light. Can everybody see that? It's for the living room only. So all we've done is we've said if 40% is equal to 100% of the room area, what's 9.47 meters squared? That's the area of ventilation. What's that equal to? It's equal to X. We just do out the calculation, and it gives us 23. My point isn't very big there, is it? 0.6%. So in this living room area, we have, of the floor area, we've got 23.6% of that as openable area. What does the NCC tell us we have to have? 15.
So in the current 2016, it's got 10.
Yeah.
So down south they don't have to have as much air movement.
Is that for climate zone 1?
Yeah, I think so.
Did you go and have a look at what Paul's looking at? Because I don't know what Paul's looking at.
Throw 2016 in the mix.
No.
Yep.
But it's,
That means you have to have less openings in the newer one. That's really strange. It's really bizarre they've gone that direction.
They want everybody to use air core.
Yeah.
Well, actually, money.
Yeah. Looks like it's come down to 10%. This figure has changed to 10%, and this figure has changed to 7.5 in the newest edition of the NCC. However, this is the edition of the NCC that we are currently using in Darwin. So this is what, if you're designing a house today for a building permit, this is what you have to comply with.
Probably with regards to the concept you've got between ventilation and solar heat gain. Actually, can be quite challenging sometimes to get enough ventilation without getting too much solar heat gain. So might have been a downward
instigator in the So are we compliant?
yes.
What do we need to have? Without a ceiling fan, what do we need to have? Without ceiling fan, we have to have 15% of the floor area as openable area for ventilation. With a ceiling fan, we have to have 12.5%. However, I definitely think we need to have a ceiling fan anyway. Okay? We definitely want to have ceiling fans anyway, even regardless of the fact that we have lots of openable area. Yeah, absolutely. I wouldn't ever recommend designing any habitable area in Darwin without a ceiling fan. Always. It's a given, really.
The table that Sandra's created on the board is an ideal way to show the data in a concise matrix on your floor plan. So just perhaps if you create just the text in columns, then you can draw a box around it once it's finished. It's hard if you draw the box first to know how big a box you need. So do the text first and then just wrap a series of headings and lines around it just to keep a track of everything. You've got the room names on the left, their area, the floor area. Then you've got the area of openings, and then the percentage of that.
I think I'm going to have the opening area here. Yeah, opening area.
The amount of openings, yeah, in square meterage, and then what that is as a percentage.
Oh, what did I have? 9 point.
And then draw, so the icon for a fan is just a circle with a Y shape. It looks like the blade in the middle. Put a fan diagram in all the habitable rooms, and then either create a legend or put a little note next to that icon saying minimum of 900 diameter with a controller, because you have to have a speed controller as well.
And normally we would see a ceiling fan over the dining area, in the kitchen, and the living room area.
One thing that you can do if you don't have a gas stove. Gas stoves and fans and kitchens don't go well together. That's the hard way. But if you've got induction or electric, it's not too bad.
If anybody wants to take a picture of that, they are more than welcome to do it now. I'm about to rub it out and do the next calculation for the bedroom 1. Do you have your camera handy?
Yeah.
Do you just take a snapshot of that, because I might write it up on a note for next year. And we'll have to do it all again. You've probably done it 20 times. All right, bedroom 1, we've got 2 windows. They're window 6 and window 7. I'll just do it down here for those who are still writing. This is going to be for... Why does my marker only want to work half the time? Flick back to my... So window 6 is also 2.7. And window 7 is also 2.7. It's 5.4 meters squared. Everyone's gone very quiet since we started doing some maths. I'm doing bedroom 1. So window 6 and 7, I've just got the areas of the windows, which I've totaled to be 5.4 meters squared. Oh, I didn't do the 90%, did I? Silly me, I missed a step. Yeah, I just want to get 90% of 5.4 meters. 2 only has one window. So has everyone followed that along for bedroom 1? We've had 2 windows in bedroom 1. Window 6 and window 7. They both have an area, window area of 2.7, 2.7. We add these together. We want to get 90% of that total. 90% of the 5.4 meters squared is 4.86 meters squared. If 13 meters squared, the room area is 100%. 4.86 is equal to 37% of that room area. Okay? So that's the percentage of opening of the room area that we have for that bedroom. And the other two should be fairly simple. We got bedroom 2. We've only got one window there. That's W05, which has an area of 2.7. What's 90% of the 2.7? Somebody tell me. 2.43. I'm rubbing out the first bit now. What's wrong, Chrissy? Can I help you with something there? The size of the window? And the area in the room, because I took the robes in. Remember that bit? I added them in. That's why. Yeah. Sorry, you don't have to do it like that if you don't want to. And the other one is 243 divided by 11, 22. So this is a very handy little table to put on your drawing if you ever have to work that out, just the top bit. You don't need all these calculations. You just do them on a rough piece of paper on the side with your calculator sitting at your desk. But that table at the top clearly explains to the building certifier how you've worked out the ventilation requirements and the areas of opening for this calculation. And he can then clearly see compliant. You could have another column that says with ceiling fan, minimum requirement 12.5% over here, and another column that says compliant, and you'd write yes in there. So the house is fully compliant with or without ceiling fans, because as we know, when we go back to our NCC, we just need to get 15% and 12.5% with ceiling fans, and we are installing ceiling fans. So in all of the bedrooms, I would put one 1200 diameter ceiling fan. 1400 diameter, so you can also get 1400 diameter ceiling fan. Yeah.
Put little 600 ones in the toilet, in the bathroom.
Nobody has ever said in Darwin, nobody has ever said of any time I've ever put a ceiling fan on a drawing, they've never said, I didn't want that ceiling fan. Nobody has ever said that to me. So you can't go crazy with the ceiling fans. Yes?
That's a minimum ventilation in a different section of the NCC.
We looked at that last week.
Not about energy efficiency, that's different.
Yeah.
So this is more than compliant with that. but it's a requirement that's extra because of the thermal assessment, because of
So
the energy.
5% is how much fresh air do I need to be able to get into my room to stay alive and have good air quality. The 15 and 12.5% here is about cooling you. It's about getting air movement to cool you. They're two different parts of the NCC, two different requirements. Okay, and I'm going to quickly flick back to the breeze path. So we looked at, where do I have the floor plan? There it is. Floor plan. So if I was drawing breeze paths, so the other part to this is you have to show the building certifier where the breeze paths are. We've looked at the conditions for breeze paths, and we've said they need to join two windows on opposite elevations. So I'd probably draw my breeze path, and you draw it like a squiggly line with arrows on it. Probably draw it out through there. I'll probably show another one coming from here. You can use the same window twice, up through here, cross flowing that way. So our living area is quite compliant. Breeze path is definitely no more than 20 metres. There's actually no doors or anything else. There's an opening here that we can certainly use. It meets the requirements of the 1.4 metres squared of an opening that we needed to do. In the bedrooms, slightly different. So we do have a window here in the corridor, which is quite useful, and exactly why it is there in that location is to create a breeze path. From the bedroom windows, we're allowed to go through a maximum of 2 doorways. So we're only going through one here. So we can actually go through there and show our breeze path going through there. It'll be similar for this bedroom. And then the master bedroom has 2 windows within the one room. And it also can show your breeze path there. So we're definitely covered for having breeze pathways as well as the minimum opening requirements. And we don't need to borrow ventilation from one room to the other. We did look at that just briefly when we read out the notes before lunch, but so for instance, if for some unknown reason the kitchen had no window, the kitchen's a good example to take here. If the kitchen had no window and we were treating it as a separate room, if it had a doorway there, then we would calculate the area of this area and see what our minimum requirement was. We would realise that we're well in excess. I think the kitchen living room was about 23%. And then, so anything over the 12.5% that we needed, so up at 23%, we've got all of that we can borrow into the kitchen area. And for now, that's all you need to know about that you can. It's possible if you've got excess air. I feel like I'm a bit full of hot air right now. But if you've got excess air, you can borrow it from one room to the other if you find yourself falling short or if you don't have a ventilation opening in a particular room. This is the one I mentioned last week when I said when people are extending their living areas, you have to look closely at this when you're putting in new ventilation openings, that you have enough new ventilation openings to cover not only the extended area, but also the existing area of a living room kitchen.
That space is unlivable though. Yeah, that would, like great big, so they put sliding doors in as the answer.
Mm-hmm.
Well, now you can't furnish along that side, or so you've got this huge cavernous space.
Yeah,
It's
difficult to furnish, yeah. Yeah, that can happen. That can happen very easily here. I find it difficult to furnish spaces because of lack of wall space. Yeah. Yeah, yeah. Okay, we'll leave it there for energy efficiency. Now, the only thing I wanted to mention at the end is, of course, we have the 5-star energy modelling. We use software called Accurate. That is a performance method of doing all of these calculations. It's like a software that does it all for you. It sounds idyllic. It's not really. It still takes quite a lot of work to put the information in because you still have to, in that model, you still have to build up what your roof construction is, what your wall construction is. You've got to put in all the areas of all the windows. You've got to obviously look at your orientation and you build the model. The engine does all the calculations in the background. It'll tell you if you've met your ventilation requirements. It'll tell you if basically what it tells you at the end is your star rating. And we've a minimum 5 stars in Darwin. A lot of the new suburbs ask for 6-star energy ratings. I don't know a whole lot of draft people who are still doing this method of compliance. It's quite lengthy. As you can see, it's taken us more than half the day to get through it, and it's only one small part of the NCC. Yeah, it is a way of doing it. Lisa's going to hand around a set of drawings that actually have a star rating. Yeah, and as you can see on the certificate for the star rating that's been passed around there, it has all the information. It has what the R value of the walls and the roof and the floors need to be, and all the other information there. And that's so that when that certificate goes to the building certifier, he can check, he can look at it and say the walls are supposed to have X R value for the insulation, and when he's on site, he can check that that was actually installed. Okay, any questions on any of that? Everyone's happy. Everyone's very silent, which scares me slightly. Yeah. Let it stay. If you do have any further questions, please do come back to me. And so for the purposes of your report, you need to be putting in more or less that table into your report.
And run over it.
Oh, okay, yeah, no worries. So you need to have this, either this part of in your drawings and have these tables on there, or you need to have done an energy rating prior to applying for your permit to build, so your building permit. So you'd need to submit that as part of your documentation to the building certifier, because he needs to see that before he issues you with a permit to build. So it's in the design. It's in the design part. So obviously, like if you're designing a brand new house and you want to know, are my windows compliant? It's a very sort of early design question that you're going to do and start doing some calculations. You'll find that it's not, I've never found it that hard to meet the ventilation requirements of this. I have to say, you know, we're kind of used to windows and having openable areas in Darwin, and it's very rare that I've ever picked up a design for a house that hasn't met this requirement. I ran into more problems with it when I'm doing extensions and renovations than I have with new housing. Yeah.
Code expectations for commercial.
You just touched on one of my pet subjects. So, great news for all of you people who think you're doing a great job saving energy in your houses. In our commercial buildings in the Northern Territory that are fully air conditioned and don't even have openable windows, so couldn't even avail of a breeze even if they wanted to, we have no requirements in the Northern Territory. Zero. There is Section J of the NCC, Volume 1, is all about energy efficiency. It's been adopted in every other state and territory for, I think Tasmania was the last one, and they adopted it about 8 years ago. The rest of the country has had it for about 15 years. And we have not adopted it yet. No, lack of political will. The minister. Yeah. Yeah, well, I suppose they make the decision based on recommendations from the building branch. I think the building branch have been quite active in making recommendations for this, but I do think there are a lot of commercial building owners who wouldn't be a popular decision with them.
I mean, I went through a residential new development recently that went up on the architectural walls, and I feel it would meet those ventilation requirements. That would be my guess.
If it's got a star rating, if it's got the minimum star rating, which it would have had to get a permit, it would have had to meet the ventilation requirements. But yeah, they're not that onerous. They're actually not that onerous.
Half what we've got in this house.
Yeah. So you can get away with less ventilation openings. When you use the model though for energy modelling, contrary to popular belief and what's been in the NT News from time to time, it doesn't, because there's this argument, like we spoke about this morning, there's this argument between the glass in the house being the weakest part and it lets in the most heat, and it's out most of your air conditioning, and the glass being the really weak part for that heat transfer through the glazing. And so there's always that balance between having less glass because it's hasn't got the biggest insulation properties, and having more openable areas for increased ventilation. When you do use the model for your star rating, the more ventilation openings you can have, so the higher your star rating. And that has been reported incorrectly in the news to say that the star rating is making us have smaller windows. It's not making us have smaller windows. It's giving you a benefit for having less glass but it also gives you a benefit for having more ventilation openings. But of course, they both go hand in hand. You can't have more openings without more glass. How you can do it is not designing with slider windows that only have 40% ventilation openings, and fixed glass in a tropical climate is just ludicrous. It lets in all the heat, but it doesn't give you any benefit of breezes. So louvers are absolutely the way to go, because you get 90% of your glazed area is openable and can capture the breezes. Louvers are more expensive per metre square, but not vastly. Yeah.
If you go out to the toughened glass, it can get
Full moon.
If you stay within the 600.
Yeah. No, there's no such thing as a double glazed louver. There will be. Yes. But it's difficult. It's really difficult because of the way they open and close to get a double glazed unit in there. Because we don't like to open our windows out like that, because we do get like cyclonic conditions and they tend to flap around a lot. But there's not reason. You can have like French door type openings here, but you can't screen them. You can't put mosquito screens on them, and that's one of the big reasons why they're not used a whole lot. Sorry? Yeah.
Casements don't let a lot of ventilation out. They're quite bad, especially the ones that open at the bottom.
No, I mean, yeah, of course, that's a hopper.
Yeah, a hopper window, yeah, that's true. Yeah. Yeah.
They're not too bad.
Yeah. They're not too bad. If the breeze happens to be coming from the side it's out, it actually blocks all the breeze, so they're not as popular. The popular have been sliders and louvers, because they don't have those big overhangs for wind. Yes. Yes. A great solution.
We can afford that.
Yep. Yep. Slide it into the wall. Just have enough wall space. Yes, I will. All right. I am going to